take them.
Please remember them
at the end.
Yeah.
Write them down or whatever, or even put them in the comments section. But we won't see it during the presentation. Right?
Yes, put them in the comments and we can answer them at the end.
Of course. Yeah.
So I'll let you start.
Yeah. Well, welcome to the society. The first slide here is about the committee. So this has been the rundown. This is us. These are our pictures. Yeah, probably. Yeah, seen them on the Facebook page or whatever, stuff like that. Like we've just said, there's 2 more members in our committee, Anna and Deppy, who I'm sure you'll see in other events and things like that.
Yep. Just to point out, since we're starting off, a lot of these photos are from our events. So my photograph, my name is spelt wrong, but my photograph. That's one S, don't worry, it's fine. My photograph is from our annual ball, which we had in 2019. We actually had a boat cruise down the River Thames. That was great fun. Adam's, so in the middle, Adam's photograph is at Chernobyl.
Yeah, that's where we went last year as part of the annual trip, which we'll mention
our
later.
Our annual trip abroad. And Deppy is also at the end. Deppy and Anna is actually in that photo.
Yeah.
They are also on the boat ball.
Yeah.
From last year.
So this is a rundown of what we do as a society. So us as the committee are people you can go to. We will help you with anything to do with the society, anything to do with your academic studies, socially. We can also direct you to anyone in the department that you might need for help or anything like that. We've got Harvey with us here today, who's the welfare officer for SPA.
Yeah.
I think that's, yeah. So you'll no doubt meet him. You'll probably see him at other events and stuff. Yeah, exactly.
Yeah, we thought so.
So, yeah, you know Harvey. As a society, we organise socials with drinking, non-drinking events. The following slide is about some of the changes that we've had to put in place for 2020, how the site is going to run differently, but ordinarily the socials are drinking, non-drinking events like that. We've also, one of our main things and one of the things that we'll still be able to run really well will be the lectures, which we are planning for. We've got the Anthony Phillips lecture today. We've got a couple of ones planned for the future, things like that. As a society, we're involved with the Institute of Physics, the School of Physics and Astronomy here at QM. We also have connections with other physics societies, companies, groups like that, don't we? We run events with them. The annual trip abroad is a huge...
it's a huge part of the society.
It's a huge part of the society.
Yeah.
Something
and it
that
takes up a lot of our time.
It
but
does.
It's definitely worth it.
Absolutely,
it's definitely my highlight of the university year.
Yeah, and it was an amazing thing to see last year.
Yeah,
absolutely. And there's also the annual ball, which me and Adam haven't been to because we couldn't run ours last year.
Because of coronavirus, actually.
But Luke knows all about the annual ball.
That is great fun. Get all your friends together, fancy ball, have some fun. Very nice.
Always nice to go back.
And the other thing I would just quickly advertise, since we were talking about lectures, soon, not yet confirmed when, but soon we will have an interview where Professor David Berman, who will be teaching you classical physics in first semester of first year, so sort of like Newtonian mechanics, essentially, and wave physics as well. He'll be interviewing Professor Martin Perry. Sorry,
that's the one. There is something on it in a later slide.
Yeah, there is.
Yeah.
And he worked with Professor Stephen Hawking on black holes and space-time theories and all sorts of
lots of exciting stuff.
That will be great.
That's one of the events we've got coming up.
Yes.
So it won't come as a surprise to anyone that we've had to change a few things in the way that we run the society, unfortunately. This page is a little breakdown of what we've got in place. So unfortunately, the normal socials that we do, which include things like the pub crawls, bowling, nights out, are really unlikely to run. The Students' Union isn't allowing us to plan events like that. The government also has restrictions in place for things like that, so understandably.
It is tricky for us to run events like that when you can only have 6 people in a room and our events are usually much more packed than that.
Exactly.
Especially the socials. So it's just not feasible, unfortunately.
With these changes that we're putting in place, we will be reviewing them constantly based on what the union tells us, what the government tells us, and obviously we want to plan events, but we're not going to be able to do it unless we get the go ahead. So
hopefully we can get those back running as soon as possible.
Exactly, yeah.
So.
Well, when everything starts to get back to normal, these events will come back and stuff like that. So we're going to have to review that.
In terms of lectures, we will be running them online, and we have been doing that over the summer. We'll be doing it by Teams. Previously, we were using Zoom, but we are now using Teams. So apologies if there's any hiccups in technology, but that's probably one. But so far, they've been very successful. They've been great. And the ones that we recorded over the summer on Zoom have been uploaded to our YouTube channel, which you can access on our QM Plus page, which will be available very shortly.
Yes. And the advantage of that is obviously the advantage of doing it online is previously, if you couldn't come to the event, you might have missed the lecture, you might have really wanted to see it. Now these lectures and things will be available for you in your free time if you can't make the event. And
also, we soon hope to have lectures that are recorded on campus using the
Q review.
Using the cameras.
We have a camera system. We're in a lecture hall right
there's
now.
cameras in the lecture rooms. If we have lectures recorded on there, they'll be uploaded to Q review, which, in case you don't know, is the service that allows you to watch lectures from home. Usually. Yeah.
And of course, big disappointment is the 2020 trip, which is very unlikely to run this year. It's difficult enough to go abroad as a small group on your own right now. So planning a big trip abroad with 40 people, it just isn't feasible. We're going to have to look into that at Christmas, but it's not looking very likely.
But just so you know, if that was to happen, that is usually late February, early March. Yeah. So that's when your reading week in second semester would be. So
you hopefully wouldn't have missed any.
You wouldn't
lectures
miss any lectures.
You never miss lectures. Like we purposefully never schedule events during lectures or anything like that because your education matters.
So this is a breakdown of some of the socials that we have planned and the socials that we'd usually be planning, things like that. So as mentioned, this includes pub crawls, bowling, dinners out, stuff like that. These were just regular events that we used to do, monthly things and stuff like that. The lectures that we usually do, these lectures are academics in the physics department. They're people who will have been your lecturers in subjects. But the lectures usually cover content which you wouldn't ordinarily cover. They might be very specific topics. The people who are giving them are experts in their field, and it's really interesting stuff. That's why it's what the draw is, I think.
Yeah.
Really.
Essentially, in year one, you'll mainly be learning physics that is well known or has been known for a fairly long time. Nothing, brand new. Whereas at our lectures and events, you'll be being told in a more casual way as well about science that is being discovered right now, theories that are being tested, experiments that are currently going on around the world. And at the end of the day, that might, and it has certainly helped me, decide what area of science you might want to go into. Because as you come into university, I came into university wanting to be an astrophysicist. But as I went along, I decided I was more into the theoretical and lab side than the astronomy side. And most of that was because I was going to lectures, both on astronomy and on theoretical physics. And I personally found that theoretical side,
new interests.
Exactly.
Like that. Yeah.
So it will help you to know where you might want to go. Because in year one, you'll be pushed into physics and maths, certainly.
Yeah.
But you won't be able to see, quote unquote, the end goal by seeing by coming to our lectures or watching our lectures, I suppose. You'll get a much better perspective on that, I would say.
And as mentioned before, we have the Functionality from Disorder by Anthony Phillips. That'll be in
2 o'clock.
about 40 minutes.
Yeah.
He's going to be joining us.
Yeah.
There's David Berman interviews Malcolm Perry on black hole string theory and Professor Hawking. That's an event that we don't have a date for yet. I don't
Looking to get that organised in the next few weeks.
But that's going to be coming up soon. That should
Yep.
be our next event. And the end of the year ball, it's a long time in the future, so it's too early to call. But as we anticipate it, it will run in 2021. So we'll have to see that. That's something to look forward to, I think.
Cool.
So we also, as mentioned, run collaborations with different companies and physics societies and the School of Physics.
Yep.
Some of this is about getting a different perspective. When we had an event last year at Imperial.
Yeah, we have
Where
we have very close ties with the society leaders at Imperial, PsiStar, and the UCL Physics Society, and we have also worked with the King's College London Physics Society. This year we have even closer ties to the UCL one, so it seems very likely that more collaborative events will be going ahead.
Absolutely, and they've obviously got their own lecturers, which are experts in their field. We had in the event last year, Professor Richard Nelson, who you will have for Our Universe in the second semester, delivered a bit on exoplanets, and they had their own lecturers who were also working in similar areas. And it's really great to get to change scenery and get to change of perspective as well in that sort of regard.
Because of course that was the Nobel Prize for that year, so that was why we themed it that way.
Yes.
But of course we also work with the Institute of Physics. We are affiliated with the Institute of Physics. In fact, we're an affiliated society. We always encourage our members to join the Institute of Physics. It grants you loads of great opportunities. They've got loads of lectures as part of their membership that you can go along to. They do student-led quizzes, a lot of them during our lockdown, but also they have loads of careers help, and they have loads of stuff. I would heavily suggest you Google them and check out their website. And apparently they're coming onto campus in the next 2 weeks as Harvey. So you should hear about them fairly soon.
There is also some of our PhD students, which are all obviously doing their own research. We get them to do talks on some interesting areas and also tell you about postgrads, something that is probably a bit early for you to be thinking about because you obviously only just started your degree, but something that a few years down the line is definitely going to be something you'll be considering to further your education. And last of all, there is PASS, which is, I'm not sure how they're running.
Peer-assisted study support.
Yes.
I'm a PASS mentor, so I can tell you about that, in case you haven't already been told. PASS is PASS is open to all foundation year first year and second year students, and essentially it's we hire year students, year 3s and year 2s, can help you with your coursework, with questions about university, modules, whatever you want. We cannot give you the answers, but we can help you, hence it's mentoring. And it will be running this year. There is a QM Plus page, which you should be able to access when you click on all modules. And it will be accessible via Blackboard Collaborate, which is essentially like a live Microsoft Paint, sort of also like Teams kind of system, which means that we can like write on whiteboards, you can join in, and we can solve problems together in your homeworks. But as I say, not give you the answers, because that would not help you in exams at the end of the day. But yeah, I would heavily recommend year 1s and year 2s, and of course foundation years to join in, because
it's really giving you as much help as possible, isn't it? You'll eventually inevitably hit a brick wall with something, and it's really helpful. I think some of my main help during first year came from students in older years. They've obviously just learned it, it's fresh in their minds. We had the opportunity to directly interact with them, but you guys won't see as many people on campus doing that. So having the opportunity there is really helpful. Cannot overextol that enough, really. Yeah, so I think we'll.
Go on.
Oh no, sorry, I jumped the gun there.
Right. So although it is quite unlikely that we will be able to run an annual trip this year. We thought we would just point out some, well, actually that is just some of the locations we've been to. We've been to, back in 2016, went to Bergen in Norway to look at the Northern Lights, and there's lots of good photographs of that. In 2017, the gang went over to Geneva to visit CERN. We were actually guided around by our own staff, Professor Marcella Bonner. She might be professor, I don't know. But she's very influential in CERN, so we got our own tour around Atlas, and that was very interesting. In 2018, they all went to Iceland to have a look around Iceland, essentially. There was Northern Light stuff, earth sciences, they visited volcanoes and
geophysics, stuff
yeah,
like
sort of
that.
geophysics, exactly. And also obviously there's lots of, as you might have seen recently, the whole phosphene on Venus. We don't understand planetary atmospheres and how planets are created completely yet.
As well as we'd like to.
Certainly as well as we'd like to. And Iceland has a lot of what we think helped create the Earth still going on.
Geologically very active country, isn't it? So,
exactly. Yeah. Then in 2019 we went to Amsterdam and visited ESTEC in Noordwijk, which is a European Space Agency design and technology centre that's only was opened in 2019. So we were one of the first groups in the world to visit. And they had, it was great, they had like real Mars rovers, they had like the
I think there's a
parts
picture of that in the top right.
Yeah, that's right.
That's
You could like go inside parts of the International Space Station or
models.
life scale models of the International Space Station. It was amazing.
Was that the first one you were on? Was that?
That was my first one, yes. And then in 2020, we went to Kiev in Ukraine, which was great.
Yeah,
very cheap,
yeah.
And we visited the Chernobyl exclusion zone.
I think that was the first year that was available as well, wasn't it? I think they'd only just opened the exclusion zone to tourists, like the previous year.
No, I don't think that's the case.
It wasn't.
I think it was getting cheaper. I think it was getting much cheaper than it used to be.
Yeah.
Oh, okay.
Yeah.
No.
Only if you go in such big groups.
Yeah, I don't know. Sure.
No,
whatever.
But that is incredible.
It was great.
And the photo there in the middle is the one that we got as a group shot.
That's only half the group, I might add.
Half the group, yes.
Yeah, because we were split into on that trip.
You know, fashionable pink hazmat suit.
Yes, I don't know if you can see my mouse. This is Shay.
Yes.
This is Shay. So. Right, I'm here. Anyway. Memberships.
Yes.
Yes.
You can scan that little QR code there, which will take you directly to the Students' Union website. I know, I made that.
Oh, that's insane. I love that. Yeah, so you can get your memberships for the year.
Yeah.
£5 for the year, which is pretty decent.
That is probably one of the cheapest ones that there are
Yeah.
available. If you want to join any sports societies, they might charge you up to £100
Some
for
of them
the
do,
year.
Yeah.
I know Sorry?
Yeah, I was in jiu-jitsu and it was £80 a year.
Fencing was £150 a year.
That's it.
Yeah. It's so £5 a year. That £5 will be for you to attend regular lectures. If in semester B we look to do more socials, which we'd be allowed to do, then it will give you the opportunity to do that, and that essentially really helps the society run.
Yeah.
That's, I think, is our primary sort of income, really.
It's our largest source of income.
Yeah. So that's how we can get the opportunity to organise big events and collaborations and things like that.
We need your help.
So if you guys could do that, that would be really helpful for us.
Help us to help you,
Yeah. So please do scan the link.
Or click on the
it will only
link.
take you to the QMSU page for PsiStar, which has been updated for this year.
It has.
So it should have up-to-date information. We don't update that one as regularly as some of our other sites, but you will be able to find out information about our upcoming events on there. General society information. There's also our emails.
All the links in places on there, aren't they? So.
Yeah, you can email us directly if you have any questions about the society, about the university, about anything, and our university emails are all on there. So,
But in general, if you want to email the society, PsiStar, so that's PSISTAR @qmul.ac.uk. one of us will answer whatever you have to ask us, or tell us, or offer us.
Absolutely.
And we are quite quick on there, I think.
Yeah.
But anyway, so
hopefully you've clicked that link. You've scanned that
click
link.
that link.
Yeah.
Yeah.
Smash that like button.
Smash that like button. Squad fan. Right, I'm gonna go to the next slide. 3,
And
2,
the next.
1, bang.
And there it is, our social media. That is the link to our QM Plus page, which is new for this year.
Can they click on that?
I don't think they can. That is a hyperlink on my PowerPoint, but I don't think that you can click on that. So please just go to, if you go to QM Plus, there's a search icon in the top right. If you put PsiStar in there, it is the first option to come up. And that should have been available, made available. Thank you, Harvey. Yes.
If you want to be added to our WhatsApp group,
yeah, that we do have a WhatsApp group which is does have discussions in it, and you can ask for help in there. It's quite active. I don't know how you invite people to.
Yeah, so what I think would probably be best, if you want to join our WhatsApp group, which we would suggest, and also if you want to join our mailing list, because we do send out emails. It would be best, I think, if you do email us at qmsistar@qmul.ac.uk, because that way we'll have your email address, and if you give us your phone number, we can add you to the WhatsApp group.
Absolutely.
Because we do send a lot of our information out by email. I know a lot of people don't like using social media a lot as well, so we do get a lot of people asking, more emails please. So there will be more emails this year.
And usually we would have a big freshers fair where you'd be there and you can type your email in, and we'd just add everyone to a mailing list. But this year things are quite different, and we don't even know what's going on at the welcome fair. So they haven't told us that. They haven't decided what they're doing.
Oh, there's no welcome fair.
No.
There's
really?
There's an
Is there an alternative?
There's an unofficial one.
Okay. Well.
It's next week sometime.
Are we doing that?
We might do. We'll see. Also, join our Facebook group. If you go into search on Facebook and you type in PsiStar, I think, does it?
Yeah.
It definitely comes up if you put in PsiStar Physics and Astronomy, but it should come up with PsiStar on its own.
Yeah, and that is one of our that is all the most up-to-date information is on there. That is where if we have any lectures, events, we'll post a link in there which you can just click to join in, stuff like that. So the Facebook page is the most useful.
And that's been used since the start of the society back in 2012.
And that does bring us to the end of the introduction.
Yeah.
And that has run over a little bit as well. I think.
What do you
How long
think?
does the quiz take?
Well,
I think we can squeeze the quiz.
Do you think we can squeeze the quiz in there? Okay. Well, we're gonna fire up the quiz then, which we've got on the. Sorry, I have to reach over here, which is I think we're still screen sharing. Where is it? Okay.
I'm so glad it didn't tell me the answers on the screen.
Fix the beak.
Right. You set this up.
So if you want to join in, go to kahoot.it. Well, type into Google Kahoot essentially, or if you so you don't get echo. But you can join us with that code 2346675. You can join in the Kahoot.
And I think it'd be worth those people joining in now. I think it'd be worth mentioning that if this does run over a little bit, this should end no later than 5 minutes past 2, because that's when we have our lecture from Anthony Phillips. We don't keep on waiting. Yeah, we could, but hopefully we'll squeeze it in.
Yeah, we should be alright, I think.
Should be fine. And then after that, we've got the Q&A session. So do, if you have a quick check of the comment section now, see if anyone has written anything in, but...
Yeah, that's just good.
That one.
How does Teams work?
Yeah.
Chat's up there.
Chat.
Are we still showing the screen? Oh.
No.
Hello, James.
Say hi.
Thank you, James.
I don't think we are still showing the team, showing the screen.
Let's maybe do that.
Let's go to there. We are, beg your pardon.
We're back now.
Hello.
See our nice faces.
You can see us. I think they could always see us, actually.
Maybe, I don't know.
There's the number back up if you don't have that. We'll give you another 2 minutes to get that downloaded and logged on. If you don't have Kahoot, then
I've tried to make.
What are you doing?
I'm sure everyone has the Kahoot
I have
app.
tried to make my Kahoot as balanced as possible, but well, we'll see.
Yeah.
I've never seen a lot of these questions in quizzes before. They're not hard questions.
Is it
It's
physics
multiple
based?
choice.
Some of them are physics.
No, it's
most of them aren't. It's general knowledge.
Oh, good. Okay.
You know, I think people from all walks of life will quite like.
Yeah.
You'll like one of the questions at least.
At least one.
Yeah, just
By the way-
hang out for that one question.
No, you do that.
Oh, of course, I'm showing the PowerPoint slide, aren't I?
Apologies.
Sorry about that. So stop sharing, share. I don't know. Some of them are
That
probably wizard.
Yeah.
There we
That's
go.
it, yeah.
So there's the
if
page.
we apologise. We didn't know we were sharing or not. 2, 3, 4, 6, 6, 7, 5. We'll give you just a touch more for people to join.
I don't. How did 25 of them get it?
I don't know.
I don't know. Just
Yeah.
guess.
Just really listening. Just
Yeah.
really like.
Oh, they heard you say it once.
Yeah.
But
Unfortunately, you might be good at remembering numbers, but in physics, you don't need numbers. You need letters. So hard luck. You might have been using.
Have fun figuring out what PsiStar means.
You might have been. Yeah, that's true. When you find out what PsiStar is, you'll be like,
Tell us.
yeah, you might have just done physics A level and be like, wow, I know how to divide numbers. Yeah, you don't need that.
Okay, you have another 20 seconds,
Yeah,
and
20
then
seconds.
there's still a couple
think we
of
got
people
most people.
coming in. Most people are in. I think there were 37 at the start of this.
Someone's
so-
being quite meta and it's called Kahoot.
Ooh.
Someone's put the code in, sorry.
that's good.
We appreciate.
Do you think they
we
knew?
appreciate
Or did
it.
they just type
No,
into the name?
that's even more meta than Kahoot. So I think they are
Yeah.
the king or queen of meta. We like that.
Okay, hopefully you are all in now. Fingers crossed. If not, I don't know if I can join any longer.
I
Thank
don't.
you.
still can, but-
I don't know. We'll see.
No
All
idea.
right. 3, 2, 1. Let's go. Oh, you
Are we going to read them? I don't.
No. It shows you. How many time zones does Russia have? 7, 8, 10, or 11?
Like
Duh,
that.
duh, 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 duh. I'm just imagining.
You imagine the music playing. The music's catchy.
We've had to mute the music. But I'm
You can still
imagining-
bob along.
Okay, I think there were 28 people, weren't there?
Yep.
Yeah. Okay.
So.
Ooh. Yeah, it has 11. It's a very long boy. It's a long country. All right, next. Well done, Hamza. Or Hamza. Lucky Simon. Ooh, who invented?
Who invented the rabies vaccine?
I know.
Louis Pasteur, Edward Jenner,
Joseph
Joseph
Lister, or Humphrey Davy.
Interesting.
I did not know this, so I was very
I should
intrigued when I
make an
found this
educated
out.
guess.
Rabies vaccination.
Mm.
You know, I think I could eliminate 2, but I don't think I.
It's Louis Pasteur.
Ah.
Edward Jenner invented the smallpox vaccination, not rabies. Joseph Lister invented sort of
Like the
antiseptic.
Yeah, antiseptic.
And then Humphrey Davy basically sniffed chemicals and discovered, and as such discovered
Yeah.
ether. It was ether actually.
Oh, was it?
He discovered ether, which
It does the same thing, doesn't it?
essentially,
Yes.
not as good, but
It's on a roll.
history GCSE. What was the name of the first Doctor Who? John Pertwee, Patrick Troughton, William Hartnell, or Peter Davison?
Let's see, how many nerds do we think we have?
Glad it was multiple
Well,
choice.
if they're physics students, there should be some nerds here. I mean,
There's
come on.
got to be at least a few.
Yeah,
At least one.
I need more.
I expect to see at least 50-50.
Oh, wow.
We got-
I wouldn't have
16
got that.
of you. Well
that's,
done.
That's a fair proportion of nerds.
That's good.
That's good. F's in the
Alright.
chat for everyone
There
else.
we go.
Lucky
Sam
Sam
is
is
doing
doing well.
On fire.
Okay.
There we go.
Name the world's largest island. Madagascar, Greenland, Australia, or Honshu?
Get this one.
Depends, because I think this essentially comes from, do you know what the definition of an island is? What counts as island?
I don't know.
There's only one answer.
I feel like a wrestling commentator at the moment. Oh my
In the
god!
red corner.
Oh my god!
That was an amazing SmackDown.
Greenland.
It's Greenland because Australia is a continent.
It is, yeah.
And in case you didn't know where Honshu is, because someone asked me the other day, it's the biggest island on Japan, I believe.
It is.
That's the mainland then, isn't it?
Yeah, I think. I know it's in
It's
Japan.
the one with Tokyo as well.
Yeah. Right.
Which garden was one of the 7 wonders of the ancient world?
Garden of Gethsemane, Garden of Eden, the Great Garden of Alexandria, or Hanging Garden of Babylon?
Said 5 knowledge coming in handy.
Hmm? Yeah, but don't worry.
Oh, don't worry, no.
They're quick.
Like this.
They are quick. I mean,
We will have to see how.
We can end
what
early
is
if we
it?
have to.
Yeah.
Good.
Hang
People
on,
playing
Babylon.
Civ 5 know their stuff. Or Civ 6, actually. Very nice.
Yeah, let's
How'd
fight
you
through
get it?
this. Yeah, we're gonna have to keep it.
Yeah, we're just gonna have to keep going. Name the famous gardens 10 miles outside of London. London knowledge here. Hampton Court Gardens, Newcastle Gardens, Kew Gardens, Oxfordshire Gardens. Yeah, there's not a lot of photos that you can
Stock
choose.
images,
on
isn't
this.
it?
Yeah, it's stock images, I'm afraid.
Depends how you play this game as well, doesn't it? I mean, do you go for the quickest answer as possible, risking that you might be wrong? Do you think about it to get the right answer?
You've got to go quick because that's how you win. Nice.
Kew Gardens, well done, 17 of you.
Lovely. Right, I'm just going to skip forward.
Some strong general knowledge here.
What is the most watched video on YouTube?
That's a good question.
Baby Shark Dance, Shape of You by Ed Sheeran, Despacito, Louis Fonsi, or See You Again, Wiz Khalifa featuring.
That's a really good
I can't read the rest. There's a thing in the bottom of our screen.
I thought it was.
No one's
Keyboard Cat.
answered.
I thought it was Keyboard Cat. Oh, suddenly
Jesus.
everyone
Again, nice.
answered.
Everyone answered
There
in
we
1
go.
second. Flat. Nice.
Despacito, is it?
Alexa,
That's
play
news to me.
Despacito. This is so
Whoa,
sad.
whoa, whoa, hold on. Some of them probably have an Alexa in the room, which is now.
I'm so sorry. If that just actually.
Alexa, answer all the questions for me.
Which heavyweight boxer was never defeated after 49 fights? Mike Tyson, Muhammad Ali, Rocky Marciano, or Sugar Ray Robinson?
It's a very good quiz.
The pictures will be great.
Surprisingly, that stock picture actually fits
Nice.
quite well. Oh, look,
Oh, we got 29. Sorry. I
So
didn't-
there is a 29th person.
Okay, I won't skip when I see 28 now. Okay.
Oh, Rocky.
It was Rocky Marciano, who is obviously the inspiration for the real one. Which player played for Liverpool, Everton, Man City, and Man U? Kenny Dalglish, Yaya Toure, Peter Beardsley, or Steven Gerrard?
I'd say just in general, based on what we've now determined our demographic to be, this question may not be answered quite as well.
I know.
That's the point. He knows the answer, so I think some of them.
Oh, wow.
Couldn't
Oh,
have been any
well
of the
done.
others.
Wow.
No, the others are either just Liverpool or maybe
Yeah.
just like Man City, I think.
Liverpool, Man City, and just,
Right. When playing music, what does a piano instruction mean? As in Italian, to play slowly, softly, to add a pause, or to play loudly?
piano.
Piano, piano,
Piano.
piano, piano. Any Italians here? You've got this.
PP, very hard.
Piano.
Very soft.
So funny.
You're wrong. Well done.
There we
Oh,
go. See, most of
I-
you there. your
Most
music
of you
knowledge
are
is
classical
up there.
musicians. Well done. Lucky Sana. doing
Join the
well.
orchestra as well.
How many valves does a trumpet have?
Ooh. That.
Yes.
Mhm.
I know.
You're whispering it like people won't figure it out. No one's there going, I can't believe this.
I cannot
What
believe
sort of a
what they
B-Tech
have done.
Would everyone get it
quiz is
right?
Well done. Okay. I mean, I would struggle to think
I
of
wouldn't
that.
have known
I might have done 4. I don't know. Well done, Drew. When painting with tempera, what is tempera? Paint with vegetable oil, paint with egg yolk, paint with sand, or paint with water? It's when you mix it in. You mix something into the paint,
Right,
essentially.
Tempera.
So you mix something
Playing with
into the paint.
tempura.
I don't know how you pronounce it. I'm sorry. I think it's tempera. It might be tempera. I don't know. It's probably an Italian word. Good.
Egg
Well
yolk.
done. Some of you.
What does it do? Do we know what it
It
does?
thickens it up.
Oh.
Thickens it up. Some of you are artists. Who owns the most followed Twitter account? Barack Obama, Donald J. Trump, Katy Perry, or Justin Bieber?
Follow Donald Trump just for the memes.
I think it's those two lobsters on screen. Don't you agree?
I don't know why the lobsters are there.
I couldn't find anything that I thought matched. It's Barack Obama. Yes, ex-president of the United States. We got.
I'd follow Obama.
Malvolio features in which Shakespeare play. I have played this person on stage. Twelfth Night, Merchant of Venice, Othello, or A Midsummer Night's Dream.
Do you have a video?
I have photos.
I'd like to see those when we're finished.
What year did you play that?
2017, I think.
Oh.
Yeah, just before I came.
Oh, nice. I've never seen that one.
It's my favourite because I was in it. He's a comedy character, also a tragedy character. Right. He gets locked in a box. Who wrote the Twilight series of books? Suzanne Collins, Jacqueline Wilson, Julia Donaldson, or Stephanie Meyer?
I'm disappointed that I know this.
Me too.
They had a lot of
Team
stock,
Edward.
they had a lot of stock wolves when I was making this. I didn't struggle for wolves. May Queen, Wisley Crab, Fox Whelps, and Lane Prince Albert are all what? Potatoes, apples, pears, or strawberries?
That's what you said before, wasn't it?
I may have said about this to you.
Yeah.
Okay. It's a good quiz though. This is making me think. I'm like, I should be playing along.
Apple.
Yeah.
All you people that fell for potatoes, never trust me. What colour is absinthe?
Ooh.
Usually. There are actually other colours of this. I've actually found out after having made this.
Have you ever had it?
I haven't, but I think I've seen it.
Yes, I have. It is now legal, by the way. People think it's not legal.
Oh, really?
It is now legal.
Does it taste off?
I don't want to say just in case it gives it away.
Yeah, I thought so.
Oh, interesting.
Green.
I'm not sure I'd want to drink anything.
There is now red absinthe, admittedly. I will give you that, but it's quite rare. I didn't find my place to
drink it.
Hello.
Hello there.
Hello. What is the most common colour of toilet paper in France? Red, blue, yellow, or green? I didn't know that other countries had different colours of toilet paper.
I'm not sure I want a different colour of toilet paper as well.
Why?
I don't know why you would bother.
No.
I know, but when I found this out, I was...
Also, is that not a question of which colour do you hate the most? Because if you wipe with
red,
people have your favourite
they
colour.
have red toilet paper in France. I can see how that would go wrong. I'm not going to say anything. Quiz. Which of these is a place in the UK? Red.
Belen strikes me as a very British place.
I see that. I see it.
Thank you.
All of them.
We just thought we would educate you. That was all.
That is fantastic.
More you know.
Which of these is not a name for a place?
You're gonna read them out.
Oh my god!
No, that yellow one, that is a place. Right, I know that yellow is a place. I'm not sure about the other side. The other three.
We can hear you.
Just muted himself quickly.
He's like, damn, I've given the answers away. It's that place, which is actually German for like a boat company or something.
Interesting.
So,
Right,
well,
sorry, I am kind of late. Oh, and I'm stupid. What am I supposed to do?
So you're supposed to have on your phone. There's the Kahoot app, and you can join using a code.
Unfortunately, I don't think the code's up anymore. No, sorry, I beg your pardon. The game pin is at the bottom.
It's at the bottom. 2,
So
3,
if
4,
you
6, 6, 7.
try joining there, you should be able to get it.
Which Apollo astronaut did not step on the moon? Alfred Gordon, Michael Collins, Alan Shepard, or Jim Lovell? I've actually met one of these. Yes, I met Alfred Warden. All of these are Apollo astronauts, but only one of them is Apollo 11. None of
you guys all students? Or...
Yes.
Yeah.
Yep.
Right. Okay.
Right, moving on. Who's winning? Lucky Sana still
Lucky Sana
winning.
back in the lead.
And Drew Takeshi 69 and Dylan SP. quiz. How many years did the 100 Years' War actually last? 99, 100 years, 102, 116 years. Bit of history knowledge for you.
We've got 10 minutes left here.
Well,
Maybe cut a little bit short, but how is Anthony Phillips joining us?
he should be joining the call.
Is he going to join the call?
That's what I asked.
See. Okay.
We're about halfway through and it's been 10
Yeah,
minutes.
we can.
So.
I can just get through this quickly. How many days were in a Roman week? 6, 7, 8, or 9?
Answer quickly. They're all named after gods, aren't they?
Not all of them.
No, not everyone, but their week was all named after.
Yeah, like Woden's Day is Wednesday. They had next.
8 people got the correct answer, which was 8. Incroyable. On average, in the Major League Baseball, how many pitches is a ball used for before being binned? 3, 5, 7, or 9 times? I.e., how many times is a ball hit in MLB before it's thrown away?
Ball.
Yeah.
Those are all low numbers, though.
It's wasteful.
Just from like.
Well, it's actually, this is the thing though. It's not even when it's hit, because most of the time, only about 30% of the time the ball's hit.
Oh yeah, maybe. Well done. 7 people got 7. Brilliant. Okay. So, which country hosted the 1986 Football World Cup? I should have made that clear. Spain, Italy, Brazil, or Mexico? Who knows their World Cups? I know a lot of people do.
I think I know that.
I don't.
Quite sure.
I'll be honest, I didn't know this either. I'm not.
It's tough even if you're.
I am myself. I'm not a big footy guy, but.
Didn't we used to have a football team?
I thought it was next.
PsiStar did used to have a football team, yes, but I'm not a big football person. True or false? Do penguins have knees? Penguins have knees, true or false?
Oh.
Does anyone know the answer?
Oh my god, you'd have to lift one up to find out.
I know.
Someone just runs to the zoo and examines a penguin.
Bang! They have knees, but apparently they're below layers of fat, so you can't see them.
Interesting. So they get much use then?
They do walk a long way to penguins.
Mm.
In what country are books given as gifts on Christmas Eve? Norway, Poland, Iceland, Czech Republic, sometimes known as Czechia.
Is it?
Yeah.
Oh, really?
Yeah. So Czech Republic or Czechia, but whatever. Norway, Poland, Iceland, Czech Republic. I have been to one of these countries, Poland. It's Iceland.
I've been to Iceland.
Bam. Yeah, I think that's nice. Better than in England, where you don't get anything on Christmas Eve.
Actually, I always open presents.
Get lots.
Christmas Eve.
Fair. You get lots of suspense.
I can see the presents watching.
Who had the UK Christmas #1 in 2000? The Teletubbies, Bob the Builder, Craig David, or George Michael? Is that Avril Lavigne? I actually can't tell in the photo.
No idea.
Or whatever, who knows?
Bob the Builder was hugely popular.
Huge.
But
I mean, all of them.
Does
were.
it count? But as a Christmas #1.
And what if George? Yeah,
It was, yeah.
Oh my god.
I was hoping you might think that.
Who's there around the Christmas tree just bopping out? Can we? Yes, we can.
Where is it to tradition to eat KFC, Kentucky Fried Chicken at Christmas? China, Canada, the Philippines, or Japan?
I can't see why you'd want to, if I'm honest. I look forward, like, for months to Christmas dinner.
I believe this country also eats Kit Kats on Valentine's Day.
I could get behind that.
They're very big on
When I'm
advertising.
alone
campaigns.
with my Kit Kat.
What Instagram account has the most followers? Instagram at Instagram, Ariana Grande at Ariana Grande, Dwayne Johnson at The Rock, or Cristiano Ronaldo at Cristiano.
You follow any
I
of
think
them?
I know that.
I don't follow any of these. I'm not.
I follow The Rock.
Ah,
Do you?
Yeah.
it's actually Instagram.
Why? Do they?
People follow Instagram on Instagram.
Why would you want to follow
do that?
Instagram? What is Instagram posting that's?
What food is stolen from shops most across the world? Chicken, rice, eggs, or cheese? We had this one last year, but I put it in again.
I'm trying to remember it.
Yeah.
I'm trying to think why you'd steal any of those. But
Not a high value item.
yeah.
What do people want from supermarkets?
Jeez.
It's cheese.
It's cheese.
People
People
love
steal cheese.
Apparently, that's a thing. There's actually studies on that. Which of these is not a member of the Travelling Wilburys? That's a band. Bob Dylan, George Harrison, Tom Petty, or Pete Townsend? All of these are legends, I'm sure you know.
Yes.
And they made the best group of
Travelling
legends ever, essentially, people say. So
Big music guy?
I'm big into music. Yeah. I have a music blog. Follow me on Instagram.
I've seen your Instagram
Pete-
story.
That is the biggest plug I've ever heard.
Yes, and I don't mind.
Shameless.
Which of these is not a David Bowie song? Aladdin Sane, Man Who Sold the World, Nursery Crime, or Sound and Vision? I do like all of these. I must say. I do like all of
Do
these.
like Bowie.
I mean, Bowie's my favourite, I will say that.
Yeah.
I'm not one of those people that's like edgy and stuff.
Yeah.
Nursery Crime is an album by Genesis in their early days, not by David Bowie. So, Lucky Sana still doing well. Who played James Bond in A View to a Kill? Sean Connery, Roger Moore, Timothy Dalton, or Pierce Brosnan? I like.
A guy says to Sean Connery, what times? When's the next train to Wimbledon?
A View to a Kill has a great theme song by Duran Duran. You should listen to it. Who rapped Juicy? Who knows? Come on. The Notorious B.I.G., Tupac Shakur, Juice WRLD, or Drake?
I do like how the theme of this quiz has gone. Because last year, Adil's themed quiz.
Yeah, he was terrible.
That was awful. Just all cultural world stuff. Just no one getting the answer.
Yeah, I tried to be good this year. Good, people knowing Notorious B.I.G. The Thomas the Tank Engine version is the best, let's all be honest. Oh, I just saw someone took over the lead, I didn't see who it was. Who painted Swans Reflecting Elephants? Pablo Picasso, Frida Kahlo, Salvador Dali, Remy Magritte.
There are so many scientists that you come across in your course that are from different parts of the world, and
Yeah.
you watch every lecturer try and pronounce their name in a different way.
Well done, it's a good painting.
Baxendale.
Tekashi 69. Oh my god, out of prison and winning. Which classical composer has two skulls in his tomb? Joseph Haydn, Frédéric Chopin, George Friedrich Handel, Antonio Vivaldi. There's a whole story to this. I knew that you were, so I thought I'd stick them into you. But you might.
Really, general knowledge.
Yeah, I'm trying my best.
Diverse.
Yeah, there are some science ones, but they're mainly at the end. Tekashi 69 is doing well. According to Statista, which clothing brand has the highest brand value in 2020? Zara, Nike, Adidas, or Lululemon? I couldn't find any good photos.
Nike or Nike?
Nike, I think it is actually Nike, but I always say Nike.
I say Nike as well, but I mean, it's
I think
just,
the
it's just divisive.
The company came out, but like with British. Aluminum. Get that out. Yeah. Nice. Not much change. Roughly how many more bones do babies have than full-grown adults? That's humans. 50, 80, 100, or 150? They got a lot more bones in the skull, you know?
It's because the skull isn't fully formed and then it solidifies in the first few months.
No, it's the teeth, isn't it? Because they store all the extra teeth.
Yeah, I mean, there's that as well.
Because I would have thought, apart from that, they have less. Because as we grow up, the bones actually like separate.
No, it's in your skull because that's why babies have like cone skulls sometimes. Because I think we might just get through. Which planet spins oppositely to the other 8 planets, except Uranus, which is completely off axis? Is it Venus, Earth, Mars, or Jupiter? I didn't know this.
I did.
I'm surprised because we did a whole course about planets and that just wasn't mentioned. So
Yes.
Yeah.
I'm racking my brain now as well, trying to.
I think you mentioned
just
it.
now I know.
You mentioned it in our university.
Tis Venus. Venus, the crazy, possibly life-living planet.
Yeah.
What is the most streamed song on Spotify? Rockstar by Post Malone, Shape of You, Ed Sheeran, Closer, One Dance, really big. I like some of them.
2 o'clock, so 8 probably join. I'm going to blaze through these
We're
last
just
8
blazing through,
questions.
sorry. How many bits in a byte of data? 4, 8, 10, 12. Who did computing A level essentially? I didn't.
Sorry, I'm just a nerd.
Yeah, chemistry, French AS. Languages are cool. The process of getting output from a laser to excite an active medium is called what? Priming, raising, pumping, or blooming?
How many of them are actually going to know that?
That's part of the fun of it.
Yeah.
Yeah. If you gave this to Peter, the lab guy, or Sakib, they would know. So it's fair. It is pumping.
Oh, the lab technicians are amazing people.
Oh yeah,
it's so sad you won't meet them.
Who co-founded Yahoo? Dennis Ritchie and Ken Thompson, David Filo and Jerry Yang, Vince Cerf and Robert Kahn, or Steve Case and Jeff Bezos?
I thought it was David Philo and Andrew Yang, the presidential candidate, and I was like, that can't be right.
Well done. Some people fell for my trick of having Jeff Bezos in the picture. Right. In which film does Matt Damon not need to be rescued? The Monuments Man, The Martian, Interstellar, or Saving Private Ryan?
Sorry?
I think I just got a message from him. If you can, maybe.
It's a process of elimination, that one.
Kreplach is Klingon for what? Battleship, dam, warrior, or... Nah, that's not a Klingon word. Sorry, we're just going to quick check something.
I think it's share the same screen.
Okay, one second.
Let's say hello to Anthony Phillips.
Hello to Anthony
we'll
Phillips.
be
We'll be there with
you in 1 second.
1 second.
Sorry, all the message says is you don't have to rush, take your time. So don't worry.
Brilliant, thank you.
Thanks.
Okay. He's a great guy, Anthony Phillips. You'll soon see. Right, here we go.
Last 3 questions.
What is the sarcastic droid in Rogue One, a Star Wars story called?
it's
K2SO, R2D2, BB-8, or IG-88? All of these are droids
They're
from
all
Star
droids
Wars.
from Star Wars.
But which is the right
Do you
one?
know them all?
I don't know that one. I'll give you that. I know the rest.
Good.
Good. I like K2SO. He's great. That one at the end might be the one from...
True or false? In the Iron Man films, Tony Stark's arc reactor runs on a palladium core.
Might be the one from Solo, I think.
I haven't seen
It is. Yeah.
Boom! No, I don't actually remember what the metal is, but it's not palladium because palladium's real.
I genuinely thought it was, because I did a presentation in physics on that.
It is only in films 1 and 2 though. In number 3, it changes. At the end of 2, it changes.
What does it change to?
Supposedly a vibranium core, because it says he's discovered a new element, but they didn't know it was actually a real element by him. So.
I'm actually doubting your question as well.
Fair enough.
I think in question,
I'll be honest, I stole that from last year's committee. So
in number 1, it is.
Number 1 and like halfway through 2, it is palladium.
Sorry, guys.
Right.
If you're all talking, then this gets quite confusing on our end. Sorry.
that's all right. Last question. If you removed all empty space from our atoms, what kind of volume would the entire human race fit into? A grain of rice, a sugar cube, a microwave, or a small car? Like a Mini Cooper-sized car.
So I think most people know roughly how much empty space there is, but that is a weird general knowledge factor. That's a sugar cube.
We could fit into a sugar cube if we decided to spontaneously compact.
A sugar cube's also the size Earth would need to be to form a black hole.
And also, I don't know, I didn't include this. If you wanted, just keep us human-sized, we would all fit on the Isle of Wight.
We'd also all fit inside the Grand Canyon.
Yeah, with a lot of space to spare as well.
Yeah.
The winner
You wouldn't fit.
Congratulations.
Lucky Sana, Dhruv, and Takeshi69. Well done. And
Well done to
one
runners
and
up.
someone else,
Yep.
runners up. You have won. Unfortunately, we can't give you prizes
We
because
would have had prizes.
we're not with you. But
What
was the prizes have been?
Event, do let us know it was you.
yes, and we
There you go.
We will
We
say,
will
well done.
give you a Fist bump, I don't know.
I don't know. Whatever.
Whatever. Yeah.
Okay.
Anyway, that was the Kahoot quiz. Thank you very much, Luke, for making that.
Yeah.
It was definitely better than last year's.
Yeah.
For how well that went. What we are going to move on to now, I'm going to stop sharing, is we're going to be moving on to the lecture, which is, I've forgotten the name of it, Functionality from Disorder by Dr. Anthony Phillips, who has joined us. Hello, Dr. Anthony Phillips.
Hello.
Yes, so we're going to be moving on to that. I'm going to share the screen over to you.
Yep.
And then when you're done, we're going to have the lecture should be about 45 minutes, maybe a bit short of that, and then we're going to have a short Q&A session with Anthony Phillips.
Yep.
And then a Q&A session with us after that on things in general. So do prepare a few questions if you want. For anyone, please don't interrupt the lecture midway through. Save your questions to the end, and then we can get to that as we go through. Sure. Yeah, so I'm going to give screen sharing to.
Welcome, Anthony Phillips. He'll teach you coding in second year.
If I just stop.
I kind of want this panel of 3 PsiStar people to be, commentating on my every move from now on. I think it's fantastic. But... All right, give me 2 seconds. Let's see if I can. Sorry.
Are you looking at?
Are you looking at?
Anthony Phillips?
Yeah.
Perfect.
Brilliant. I think we are with you, and you can go. We're going to mute ourselves, so here you go.
Yeah. Well, hey, here we go. Can you unmute yourself and just confirm you can see this and hear this, PsiStar people?
Yeah, we can see you. We can see you.
Yeah, we can see you.
Fantastic. Excellent. Well, thank you for the invitation to speak, and welcome to all the new first years. I hope you're enjoying Welcome Week. I hope you're going to enjoy classes when they start next week. My name's Anthony Phillips. I'm from the Condensed Matter and Materials group, and I'm going to tell you a little bit about my own work on making functional materials which are in some way disordered. Actually, I realized that I came to put this talk into slides that a lot of the stuff from my own work that I wanted to talk about gets quite technical, so I've left it till the end. And until that, I'm going to sort of tell some stories about where all this comes from historically and scientifically. I should just say, just in case anybody's thinking of taking notes, please don't worry. This is not supposed to be serious. This is not supposed to be a lecture. This is supposed to be some interesting stories about science. So here we go. I'm actually going to start with a really fundamental question, which is, do atoms really exist? And of course, I hope most of you will agree that the answer is yes. But about 100 years ago, maybe a bit longer, the turn of the 19th to the 20th century, it really wasn't quite as obvious as that. Chemists certainly said yes. There was this idea of what was called the law of definite proportions. So sometimes you could get the same reactants to react under different circumstances. For instance, you could burn iron in limited oxygen versus iron in excess oxygen. And they found out that when you did that, the ratio of the oxygen that was taken up by the iron was always the same ratio. It was always 2 to 3. And that was quite difficult to explain unless you said that there were some sort of small particles that we might call atoms, of which for every 2 that went in the first time, 3 went in the second time. So chemists were quite on board, as you might expect, with the idea of atoms, but physicists weren't so sure. You may have seen a diagram like this before. This is, of course, the Michelson-Morley interferometer, which was the device that was used to prove that the ether, this mysterious substance through which electromagnetic waves were supposed to travel, didn't in fact exist. And so physicists were quite used to the idea that we could have these nice physical models, mathematical models to represent physical reality that didn't have to be literally true. We could think of electromagnetic radiation as a wave without there actually literally being an ether that it travels through. So perhaps matter behaves as if it was made of atoms, but atoms themselves maybe were just a convenient mathematical trick. Maybe they weren't actually real. Einstein had an answer. So this is work he did, in fact, but before the stuff he's really famous for, the photoelectric effect and relativity. This is about Brownian motion of particles in a still fluid. It's a simulation here on the right, and the yellow dot there is just following one particular particle as it moves around. And the idea here is that my yellow particle in the simulation is something like a grain of pollen, and all the black dots buzzing around are things like atoms, things like molecules in solution. And we can't see the individual molecules under a microscope, of course. But if you look at pollen in water, for instance, under a microscope, you can see the pollen grains moving around the place, and they follow these weird sort of random walks, what's called Brownian motion. And the explanation that Einstein came up with, that which is correct, is that because at any given moment the atoms are going to bounce perhaps more off one side of the pollen grain than the other, just by random chance, that's going to create a force in one particular direction, and so the pollen's going to wander around because it's buffeted by all these molecules. So it's sort of indirect evidence for the existence of atoms, even though we can't see the atoms directly, which is very nice. But again, we'd like to be able to see them with our own eyes. And that came with the work of this fellow, Max von Laue, who won the Nobel Prize in 1914 for his discovery of the diffraction of X-rays by crystals. So he realized that if crystals, if atoms were real, they should be packed together around about 10 to the minus 10 meters apart in crystals. And he hypothesized that actually we could use those crystals as diffraction gratings. You may have seen lasers go through a diffraction grating. They're just a regular set of lines etched into some slide. And if you shine a laser through the grating, then you get a regular set of dots produced by diffraction, dots of laser light. So he thought you could do something similar with these mysterious rays called Röntgen rays in Germany, or called X-rays. And he managed to get a diffraction pattern. So in the top right-hand corner here, you can see that, it's a very, very blurry picture by today's standards, but you can see that there are these individual spots formed when he shines X-rays on his crystal and exposes a photographic film to him. And actually, he used that to demonstrate what X-rays were. Nobody was quite sure what this mysterious form of radiation was, but the fact that they diffracted from crystals, and the fact that if atoms were real, they had to be about the right size, about 10 to the minus 10 meters apart in those crystals, meant that he could show that X-rays had to be radiation with wavelength about 10 to the minus 10 meters. But in fact, it was soon realized that actually running the experiment, if you like, the opposite way around logically was even more powerful. So rather than using diffraction from crystals to explain what X-rays were, we could diffract X-rays from crystals to work out what the crystals were. And that's what these father and son team, William and Lawrence Bragg, did, and they got the Nobel the very next year. Let me go back a slide and just tell you exactly what I mean by a crystal. I'm going to come back to this in a moment, but the key characteristic, the key that makes it behave like a diffraction grating, is you have the same sort of arrangement of atoms. You can see I've got green and red repeating here over and over and over again, repeating in the X, Y, and Z directions all the way through the crystal. In other words, large enough to make a macroscopic object. And it's that repetition, that symmetry, that meant that this diffraction was possible. We'll come back to that idea in a moment. Anyway, so here's some more diffraction patterns. You can see these spots were a little bit less blurry by the time that these two got involved. And this is a comparison between the experimental, this is a photograph, this is literally a photographic plate exposed to X-rays, and the theory of how those spots might behave here. And you can see that if you sort of rotate the pattern at the top a little bit, it matches up with the one at the bottom. just because I've been showing these horrible blurry old pictures, let me jump ahead a little bit and show you some of my own data. It's collected. This is actually neutron diffraction data collected on the Koala instrument at the Australian Centre for Neutron Scattering, which names all of its instruments after Australian native animals. And you can see that with modern detectors and modern equipment, I'm using a crystal much smaller than the Braggs or than von Laue used, and yet I'm getting these beautiful sharp diffraction spots. You can see that if I wanted to measure the position or the intensity of any one of these spots, they're all beautifully separated and well defined. I can measure them all separately quite nicely, and of course that's exactly what I wanted to do in this particular experiment. So we moved from crystals. These two were looking at mineral crystals, which were the crystals that were big enough to diffract reasonably weak X-ray beams from. But by the time we got to the 60s, and this is Dorothy Hodgkin who won the Nobel Prize. By this time she was looking at biochemical structures. So one of her famous examples was vitamin B12. And so we were moving from naturally grown crystals that can be quite big to artificially grown crystals that you might grow in a lab that were only millimeters or less in size. And we're able to tell where the atoms are by this relationship, this diffraction relationship that happens when you shine X-rays on a crystal. And this is the sort of structure that we get out of biological X-ray diffraction data these days. So this is a tremendously complicated protein structure. So I haven't even shown the individual atoms here. For instance, these helices here are particular arrangements of amino acids that are joined together into the protein. So this is a very large scale structure. There are thousands and thousands of atoms here, and yet we can still use the same technique to discover the structure. So X-ray diffraction methods in general have been tremendously powerful in determining the structure of materials, and they're incredibly important. I want to take a little step back now, though, and ask, why should atoms pack together into crystals in the first place? And the simple answer really is just that every atom is the same as every other atom. If my red atom here is happy being above one red atom, below one red atom, next to a black, then this one over here is also going to be happy being in the same environment, and so is this one, and so is every red atom in the crystal. So it makes sense that you should get the same sort of pattern repeating over and over again, if each atom behaves the same. So here's a really simple example. This is a generic sort of curve for the energy of attraction between two atoms, and you can see if you push them really close together, they don't particularly like that because the nuclei are both positive charged, and the energy goes off to infinity because Coulomb says you can't put two positive charges together happily. And if you pull them a long way apart, then the energy goes to zero. Of course, there's no interaction at all, and in between there's some sort of distance where they're really quite happy to be together. There's an energetic minimum. And in fact, this idea was first looked at by Kepler, who's now, I guess, more famous as an astronomer. He had things like Kepler's laws of planetary motion. But he also wrote this treatise called On the Six Angled Snowflake. And he was thinking about the structure of snowflakes, and he looked at them under a microscope and realized they were six-sided. And he thought about packing spheres together, and he discovered, he wrote down, obviously people had known this before, but he wrote down that if you pack spheres together as tightly as possible, you get this nice sort of hexagonal pattern forming, and that's not a hexagonal pattern that's been imposed externally, and it's not there's some hidden hexagon inside a sphere. It's just a geometric fact of two-dimensional space, really, that if you put spheres together on a plane, then the closest way to pack them together is in these nice hexagonal structures. And in fact, that's obviously true, but that is the basis for many packings of atoms as well. We want atoms to be close together. They all want to be at that nice stable equilibrium distance from their nearest neighbors. And if you do that, you get much the same structures as Kepler's talking about here. And so this is an example of a sort of symmetry, which is important, which is a very important concept in looking at crystal structures. So actually, let me say a few more words about what sorts of symmetry are and aren't possible. And this leads to a different story, which is a bit of a sidetrack, but it's such a good story I can't resist telling you. So I've got at the top some packing of some simple polygons, regular polygons. So a equilateral triangle packs very nicely to fill the plane. A square packs nicely to fill the plane. A hexagon packs nicely to fill the plane. If I try and do this with a pentagon, I can't do it. There is no arrangement of pentagons which tiles the plane. That's a sort of mathematical fact of geometry. And so what that means actually is that this sort of threefold, three corners symmetry and fourfold symmetry here and sixfold symmetry are all very, very common to see in a crystal structure. And the pentagon is not. So it was therefore a tremendous surprise to a certain bunch of scientists in the 70s to start discovering crystals which looked like that, which have beautiful pentagonal faces on this icosahedral crystal, or indeed diffraction patterns. This is an electron diffraction pattern that looks like this. If you count the points there, you see you have a beautiful 10-pointed star. And this was a tremendous surprise and a blow to the scientists who discovered it, because it was thought that such a thing was geometrically impossible. If we understand how crystals work, we thought, because of the same thing repeating over and over again, and the same thing repeating over and over and again gives you threefold and fourfold and sixfold symmetry, but never fivefold. So what's actually going on? So this is the guy who did it, Dan Schechterman, and he also won the Nobel Prize for it, for discovering what are now known as quasi crystals. He wrote down in his lab book at the time, he's stuck in this diffraction pattern and wrote, "In Hayakazot, there is no such creature," because he was so confused that there could be some 5-pointed diffraction pattern. So what's the answer? It turns out actually to be related to what are called the Penrose Tilings. Actually, if you've been on campus, you might have seen these on the side of the maths building of Queen Mary. But the Penrose Tilings are named after Sir Roger Penrose, and they're a setting of tiles that tile the plane, but that never actually repeat themselves. So I can continue this pattern indefinitely out to tile the plane, but I can never actually translate it, move it, so that it ends up in a position that's equivalent to where it started. In other words, if I take two copies of this and move one with respect to the other, they'll never line up again unless they're where they started. That's a little bit difficult to describe in words. Let me show you what that looks like in pictures. Sorry, here it is. I've taken two copies of the Penrose Tilings here, and I've put one on top of each other in various orientations. And you can see when I do that, some of them line up, but some of them don't. You can see these dark bits are actually where there isn't any line up. And in fact, no matter how you arrange your atoms and arrange your patterns with respect to one another, you never get you never get them lining up with each other. In other words, there is no long-range translational symmetry, unlike what I've been referring to as a crystal. So how do we get this? I mean, I started out with this idea that atoms like to be in similar sorts of situations. So if one atom happy being in a particular environment, the next atom will be happy being in the same environment. Actually, it turns out that there are local rules that can be obeyed to generate this sort of quasi-crystalline pattern. So here's an example. On the left here, we have the two sorts of tiles that make the Penrose patterns. And it turns out that if you want to tile these together to make the Penrose patterns, all you have to do is make sure that the red lines and the green lines line up whenever you put them together. So actually, I couldn't put these two tiles together like this because the red lines wouldn't line up here. But all of these combinations here on the right are possible ways of arranging tiles together at a vertex. So you can see we can have local matching rules. In other words, each atom just has to look at where it is with respect to the next one, and is it happy with that or not. And rather than leading to something which is long-range translationally ordered, that can lead to something that's quasi-crystalline, that has this fivefold symmetry that packs together nicely, but where there is no long-range translational order. In fact, it turns out that these patterns have been known for a long time before Sir Roger Penrose described them. So here's an example from Girich tiling in the Green Mosque in Bursa in Turkey. And you can see we have a beautiful 10-pointed star here, like the tenfold diffraction pattern, and it's a pattern that involves lots of pentagons. So these patterns have been known for a very long time, but it's again, just like Kepler and his spheres actually being arrangements of atoms, it's remarkable that these particular geometric patterns also turn out to be the arrangement of atoms in particular solids. So the story gets even actually weirder than that, because the beautiful icosahedral crystal I showed you before is an artificial sample. It's a man-made sample. And at the time that was the original work was being done, the only samples known were in fact artificial. But since then, naturally occurring quasi-crystals have been found. This is an example. It's a mineral called Schechterman, which I can't pronounce very well. And it's found in the Korat Mountains in the far let me get this right, the far east of Russia. And this is a naturally occurring quasi-crystal, which is nice. But in fact, by investigation of the surroundings it was found in, the geoscientists, geochemists and geophysicists think that actually this wasn't a naturally occurring mineral on Earth. Rather, it came from a meteor strike. So actually we have this really bizarre and to my knowledge unexplained situation where we have this mysterious form of almost crystalline packing called quasi-crystals, and the only naturally occurring examples known on Earth probably originated from an extraterrestrial source, which is interesting and bizarre and has sparked quite a lot of interest in actually just what sort of conditions would have to have been in whatever star this bizarre mineral originated from. Anyway, that was kind of a digression. Let me return to this idea of symmetry, because symmetry is important. I want to explain a little bit about why. Let's just look at the word for a bit. Symmetry is from the Greek symmetria, meaning syn plus metron, measure together. It's bits that measure the same. In the scientific sense, what it means is that I can do some sort of geometric transformation to whatever I'm looking at, and I get back what I started with. So in the case of a spiral like this shell, if I zoom in the right amount, then I'll get a spiral that looks like what I started with. Here we've got rotational symmetry. If I take this petal and rotate round by a fifth of a turn, I get more or less what I started with. That's we've already seen rotational symmetry in this talk. This is an example of translational symmetry, which we've also talked about. If you move over a little bit, you end up with something that looks like very much like where you started. And of course, here the Taj Mahal has beautiful reflectional symmetry. If I take the left-hand side, it looks very much like the right-hand side. And in fact, in this beautiful photograph, if I take the top, it looks very much like the bottom. So different geometrical transformations which leave my object looking unchanged. Another way of thinking about this, actually, is that an object has symmetry if I can cover up some of it, and if you can predict by looking at some of it what the rest is going to look like. So this leaf, for instance, we say is symmetrical because I've covered up one side, and you could tell what it was going to look like just by reflection of the other side. On the other hand, an object where it isn't possible is not symmetrical. So this is an example of an object, a cat, that lacks reflection symmetry. So there is a sense in which symmetry is kind of the opposite of information. If you have an object which is symmetrical, like this fence, I can translate by a certain amount and get something that looks very much like what I started from. Then just given one single picket of this fence, I can predict what the entire fence is going to look like. On the other hand, if I have an arrangement like this where my toothpicks are different colors unpredictably, I can't start from here and predict what the next one is going to look like. I don't know what the arrangement of colors is going to be. So conversely, I could invent some sort of code where a green toothpick means A and red followed by yellow means B. and I could encode information using this system because it's not symmetrical. Whereas on the left-hand side, because the system is so symmetrical, there is a limit to the amount of information that can be associated with the system. And in fact, symmetry is really quite intimately linked to some very fundamental properties of physics, because, as you'll know, the laws of physics are symmetrical with respect to translation in space. In other words, if I do an experiment here, or if I go to France and do the experiment there, or if I go to Pluto and do the experiment there, the same laws of physics ought to hold. They're symmetrical with respect to rotation in space. If I face north or face south, I should get the same results. And they're symmetrical with respect to translation in time. If I do an experiment today and do the same experiment tomorrow, I should get the same answers. I don't expect the laws of physics to have changed from one day to the next. And it turns out that those three statements are very precisely mathematically linked to the fundamental conservation principles that you know and love, or know at least. Translation in space is linked to the conservation of linear momentum. Rotation in space is linked to the conservation of angular momentum, and translation in time is linked to the conservation of energy. And in fact, if you remember your quantum theory, you may recognize these pairs of variables as pairs that are related by the Heisenberg uncertainty relationship. So translation as an x position and linear momentum as an x momentum are a pair of quantities that you can't measure precisely at the same time. Same with time and energy. This goes very, very deep into the heart of theoretical physics. I'm not going to explore that any further, but it's a nice connection. These rules are the work of Emmy Noether, who was one of the greatest mathematical physicists of the early 20th century. In fact, she's got an interesting story. Rather infuriatingly, she's both a mathematician and a physicist. She is very, very famous in both fields for completely different reasons. So, in fact, her physics work that I'm talking about here, these connections between symmetries and conservation laws, was early work that she did relatively early in her career, and she later moved on to some pure maths and achieved some very fundamental seminal results there as well. So yes, quite an incredible person. Okay, quick question for you, and I'm sorry, because of the way I'm set up, I'm not set up to do this as a poll, so I'm just going to ask you to make your choice. Given all we've talked about with symmetry, I've got here two different states of water. I've got liquid water on the left and solid water, ice, on the right. I want you to decide which of these, on the atomic level, is more symmetrical. So just take a moment or two and think of what your choice is going to be. And the answer, well, the tempting answer, the thing you might be inclined to say is, oh look, the snowflake is so beautiful, it's so symmetrical, it has to be the solid state. But actually, if you think about it, water is even more symmetrical in the sense we've discussed than ice, because there are more geometric transformations we can do. There are more things we can do to end up looking the same as where we started. So, for instance, we talked about rotation. If I sit here in the middle of my snowflake and look along this axis, I can turn 60 degrees or 120 degrees or 180 and so forth, and end up looking in the same direction, equivalent direction. But if I sit in the middle of water and look in some direction, I can rotate by any angle and it always looks the same. So actually, this has less symmetry than this does. And the process of water freezing is an example of what's called spontaneous symmetry breaking, symmetry reduction. And again, this is a very, very deep concept in physics that I don't have nearly time to go into here. But we have this sort of tension between hot conditions. If the temperature is high, that we tend to be in high symmetry phases like water. As we've said, high symmetry is associated maybe with low information. And therefore, what's important actually is entropy, this tendency towards disorder. Don't worry too much about the technical definition of entropy. You'll come to that in due course in your studies. But for now, entropy is a thermodynamic property that's associated with disorder. On the other hand, as we cool things down, we tend to go to lower symmetry phases which therefore have the opportunity for higher information content, and energy becomes the most important driving factor. Right. Okay, so I've told you an awful lot so far, and I just wanted to pause here and try and recap some of the strands before the final stretch. So I've said that atoms and molecules often pack together in arrangements with long-range translational symmetry, like crystals. That's the top diagram here. And sometimes, because of the sorts of local packing rules we talked about, they pack in arrangements with no translational symmetry, and that's quasi crystals, like the Penrose tiling on the right. The final thing I want to talk about then is the fact that atoms sometimes pack in such a way that the translational symmetry is only there on average. And the trouble with averages is that it can be very misleading. So as a hypothetical example, consider my goat here. So imagining that you're watching the behavior of a goat over time, and you photograph it. The first photograph, it's facing to the right. The second photograph, it's facing to the left. Fine, that all makes sense. If now you decide, well, what I want to know is, on average, how does this goat spend its time, and naively average those two pictures, we end up with something impossible. So this is a medieval monster called an amphispina from a medieval manuscript from the British Library. So I mean, I'm being slightly facetious here, of course, but the point is that by taking two perfectly good snapshots and taking an inappropriate average, actually I end up with something which is impossible. And exactly the same can be true of crystal and atomic structures. So to illustrate this point, I'm going to talk about probably the most famous X-ray diffraction photograph of all time, which is photograph 51, taken by Rosalind Franklin at King's. And this was the X-ray photograph that demonstrated that DNA had a double helix structure, which is an absolutely seminal discovery that famously Crick and Watson won the Nobel Prize for, and very sadly Franklin had already died of ovarian cancer by that stage. But yeah, here is that photograph. Here she is. Here's her model of DNA, and here's a sort of modern version of the same thing. Now, obviously, there is some element of translational symmetry here. There's some element of the long-range order that gives these diffraction patterns, because you can see the diffraction spots here. But if you think about it, you realize that DNA can't be a perfect crystal, because if it were, it would be a bit like my white picket fence. I could just see one strand and know what the next would be, and the next, and the next, and the next. In other words, I might have, if it were a perfect crystal, there are 4 bases which are used as a sort of genetic code. So my crystal might go ACTG, ACTG, ACTG. Great, but I can't encode a protein that way. The way to have information is to be of lower symmetry. So although on average this thing is symmetrical, and I can go one twist up the double helix and end up somewhere that looks very much like where I started, in fact, the actual sequence of bases along DNA is not symmetrical because it encodes information. And so not only the average beautiful double helix structure is important, but also the local deviations from that average, the particular code that enables DNA to do what it does. And it's that conflict between an average structure and a local deviation from that average that my own work is based on. So in this last little section, I'm just going to tell you a little bit about some of the things that you can do with this order. Here's an example from my former student, Jiaxun Liu. When I first presented this, she was soon to be doctor, but she's now successfully graduated, so she's now Dr. Liu. And this is an example called a material called cesium lead iodide. Hopefully the structure on the right looks somewhat familiar to you, because it's the same structure I've been using to illustrate what a crystal looks like all through this talk. But you can see that the big difference is now I have shown the structure as it actually is with thermal motion taken into account. And you can see that the beautiful, simple structure where a single pattern is repeated over and over is actually only an average. You can see if you look at what's actually going on, there's a lot of disorder. Atoms are moving here and there. These octahedra are not perfect octahedra. There is a difference between this iteration of the pattern and this iteration and that iteration. So the material is interesting, particularly actually for its optoelectronic properties as nanoparticles. So here it is in lead iodide, but you can replace the iodide by bromide or chloride, which are smaller halogen ions, just the same column in the periodic table. And by choosing your composition wisely, you can get nanoparticles that luminesce in any color of the rainbow, as this rather pretty picture shows. And so these things are quite interesting for various sorts of electronic displays and light emission and sensing, for that matter. And so what Joshua did actually is look at what's called the anharmonicity in the lead to iodide bonds that allow this material to have its useful and unusual properties. So this is a histogram of what's going on at various different temperatures, just the distance between lead and iodine. Remember, on average, this distance is just a constant, just a number. But by looking beyond the average, we have a whole distribution. And you will have heard of, I think, the harmonic potential. Perhaps you may have heard of simple harmonic motion. It's sort of the simplest possible vibrational model, I guess, for two balls joined by a spring or two atoms bonded to one another. And so this dotted line, this dashed dotted line, is what you would get if you assumed the lead iodine bond is harmonic. And actually this solid line, which is quite different at lots of distances where there really are pairs of atoms, is what's really going on. So by looking beyond that average, beyond this simple harmonic structure, Justin was able to see how these bonds really behave, and hence to explain where the optoelectronic properties of this material came from. Okay, another interesting application of symmetry breaking. It's for information storage. So this is another material in the same family. You recognize this octahedron of atoms. Let's say, for example, this is a slight simplification of what actually happens, but let's say that this atom in the center is unstable there and can either move up or can move down. So that breaks, for instance, the mirror plane symmetry across the middle of this octahedron. If that's the case, I can treat every occurrence of this atom as a binary bit. And I can say up means 1, down means 0, 1, 0, 1, 1, 1, 0, 0. I'm suddenly storing information. And in fact, that's exactly what's going on inside a PlayStation. It's what's called Ferroelectric Ram. Just to clarify, I should say I didn't personally design the memory of PlayStations, sadly, but I do work on materials that have the same properties, and I'm trying to find better ways of doing the same thing. So it's back to this idea of symmetry being the opposite of information. If I can get disordered materials, maybe on average these central green atoms are in the center, but actually locally they're either up or down, then I can use that symmetry breaking to store information. You can use the same idea actually to scavenge energy. So these are a couple of examples. This one's from a metro station in Japan, and this is a demo outside King's Cross Station here in London, of trying to harness the energy from people just walking through turnstiles at the exit of a tube in order to generate electricity. And it turns out you can do this in much the same way. I'm not going to go into the details, but if these materials are asymmetric in an appropriate way, then compressing them, putting them under strain, gives rise to an electric field, which can be used to generate electricity. And so this is a really interesting and promising way of trying to reclaim waste electricity and make things more energy efficient. You don't get an enormous amount of electricity out of this, I should hasten to add. But the idea is basically just to get enough. So there are plenty of, for instance, remote sensors that you might use in scientific exploration. For instance, supposing we're trying to monitor pollution or CO2 levels in a city and stick a sensor right at the top of a tall building, it's going to be a pain in the neck to climb out there every 6 months and change its battery. So if a sensor like that can simply scavenge enough energy from its environment to do what it needs to do and send a signal back to base, that's good enough. So collecting small amounts of waste energy from the environment that might be from, for instance, vibrations from people standing on them is a useful and productive thing to do, and we're hoping to develop materials to do that. What else? This is an example of symmetry breaking in a particular atom. So it turns out a lot of materials, including the lead iodides I talked about before, have interesting properties because the lead ion actually turns out to be somewhat asymmetrical for rather obscure quantum reasons. I'll leave those till later. but unfortunately, lead, of course, is toxic. So there's quite a lot of interest in trying to generate the same sort of symmetry breaking, but from something that is less toxic. So I experiment with putting in organic molecules like this. You can see this is the shape of the lead electron distribution is kind of squashed and elongated in one direction. And so this is a kind of squashed molecule, which is different in this direction. And you have some success in using non-toxic molecules to cause the same sorts of symmetry break and hence the same sort of properties as toxic lead metal. Right, I'm going to skip this because I'm running out of time. This is what I'm working on at the moment, just to say that entropy, this idea of disorder, is also the basis of thermal cooling cycles, in particular the basis of the refrigeration cycle that every sort of cooling from your fridge to your MRI machine in the hospital is based on. Unfortunately, the cooling cycles that are currently used are based on gases which are both greenhouse gases and ozone depleters, so they're not really very environmentally friendly. So actually a big part of my research at the moment is trying to get solid state materials that in the same way can be cycled between a low entropy phase and a high entropy phase. In other words, a disordered phase and a more crystalline phase. And by cycling between those two phases, we can use them to pump heat in the same way as with vapor compression, refrigeration, but in a more environmentally friendly way. Good. So all of that was very quick. Don't worry too much about the details, or feel free to ask about them if you like. But just as an example of some practical applications of these rather obtuse theoretical ideas. Where next? So I just wanted to finish off kind of where I started. I started by reviewing the history of diffraction, and I said that we applied it first to minerals, or first of all to understand what X-rays were, then to understand what minerals were, then to understand what biological materials were. It's now absolutely ubiquitous in all sorts of science, including on Mars. So this is a picture of the Mars rover, a selfie indeed taken by the Mars rover. And this is an example of some of the places it's been visiting. This is a place on Mars that's been dubbed Rock Nest. And I think the two pictures there are, I'm sorry, I can't remember the difference between them. I think it's during a sandstorm versus not, but I can't remember. Anyway, this is the surface of Mars. And it would be really nice to know what these minerals actually are. You know, what is that sand made of? What are these rocks? You know, what is Martian geology like? Fortunately, the Mars rover actually has a diffractometer, has an X-ray machine on board it, and it has a robot that can shovel up the sand and feed it into the diffractometer automatically. So I'm just going to finish with this, which is the first diffraction pattern collected on another planet. We've got rings here rather than spots. That's because we're looking at a powder. If you like, we're looking at lots of crystals at once. So lots of spots all along this circle add up to a ring. But this is a usable and interpretable diffraction pattern, and this was reported back by the Mars rover and used to understand the mineralogy of the surface of Mars. So, where does that all leave us? Matter is sometimes crystalline, it's sometimes not. We can use diffraction methods to analyze crystals, but we need to be careful because they show us averages only, and actually the deviations from that average are also a really powerful sort of materials functionality. I'll leave it there. Questions?
Hi there. Yeah, that was really interesting. Thank you very much for doing that. So we're gonna ask any of you guys to, if you have any questions, if you did prepare any questions about that now, you can post them in the comment section on the right-hand side, and we'll read them out, or Anthony Phillips will read them. You can also unmute yourself and then speak into it. I think that works.
Yeah, if you want to
so if you want to unmute yourself to ask a question, please go ahead. Until then,
I've got some prepared. So, my first question I thought I'd ask you. I know that your research at the moment, you use lots of neutron diffraction, and I was just wondering if you tell us about the experimental side of what you do, just quickly.
Yeah, of course. So yeah, you're absolutely right. I do a lot of neutron diffraction as well as X-rays. So often that involves travel to where the central facilities are, like the koala data I showed. Unfortunately, obviously, we can't do that now. So in fact, I have a sample on koala right now, but unfortunately, I'm here in London rather than in Sydney with the sample. So neutrons are kind of difficult to make because obviously free neutrons are not found in nature. There are basically only two ways of doing it. Either you use a nuclear reactor or you use what's called a spallation source, which is where you fire actually a proton beam at a metal, and with enough energy, it sort of knocks neutrons out of the nucleus and gives you a neutron beam. So obviously, both of those things are kind of expensive, difficult things to set up. It's not like we are able to have one in our own laboratory. That used not to be the case, by the way. So Queen Mary, until the 60s, had its own nuclear reactor, which was lovely. I mean, I wasn't there at the time, but it must have been lovely for the physicists who were working on it. But sadly now, we're not allowed to have our own nuclear reactor. So we have to travel to central facilities. The UK's national neutron source is at the Rutherford Appleton lab, just on the sort of outskirts of Oxfordshire, and I, under normal circumstances, go there several times a year to do experiments. Again, unfortunately, at the moment, I just have to post samples and hope for the best. But there's also, so that's a spallation source. But then there's the European source, which is a nuclear reactor called the Institut La Langevin in Grenoble in France. That's Laue as in von Laue as in Max von Laue, Nobel Prize 14. Yeah, so there are these facilities around the world, and you basically write into them and say, this is what I'd like to do with your neutron beam. Could I have some time, please? And then there's a panel, which, in fact, I am a member of the ISIS panel. That's the UK's panel. So the panel gets a whole list of proposals, and they decide which ones sound the most interesting and the most likely to lead to good science. And they say, fine, you can have 2 days on this instrument. And then so you make your sample and you take your team to the beam line, and then for those 2 days the instrument is yours and you collect as much data as you possibly can, and then you go home and spend the next 6 months trying to analyze it.
Brilliant. Another question I have. Anyone else who has a question, feel free to bump in or put it in the chat. A question I had, since you teach Introduction to Scientific Computing in year 2, could you tell us some more about what kind of coding students are expected to do while they're at Queen Mary in first and second years, and how code and coding programming is useful as a scientist, and how do you use coding in your career?
Yeah, I mean, I guess so. There are lots of ways to use computers, but what's common in scientific research is that there often isn't a way to do exactly what you want, because what you want hasn't been tried before. It's very common. You've got a new sort of data, you need to try a new sort of analysis. Therefore, rather than relying on an existing program, you need to code your own. So what we try and do is prepare you for that over the course of your degree. In your first year, as part of the general skills course, the professional skills course, you learn some very basic Python programming. It's just a real easy introduction to the language. In second year, if you like, there's the Introduction to Scientific Computing module, which it's actually being run by Dr. Agnor this year, but I'm the associate for it. So you'll see me there if you, second years will see me there if you do that. And that is an introduction to algorithms. So it's not just literally how to program a computer. It's also what you might want to program it to do. What a computer is good at, what a computer is bad at, how to tell the difference, how to present your problem in such a way that a computer can solve it or can help you solve it. And from then on, there's a little bit of stuff in the curriculum. There is the computational condensed matter course in third year, which unfortunately we're not running this year, but in general there is. And there are some fourth year options to do with computing as well. But then of course there are the third and fourth year projects. And so it's very common if you're doing a project with any sort of theoretical basis or any sort of data analysis to have to write some code as part of that. So what would I say about how coding is used? It's It's a difficult subject. I mean, in the sense that it's a new way of thought. It's something that some people take to a lot easier than others, and that doesn't really have often anything to do with how good you are at maths or how good you are at physics or anything else. So I guess my main advice with coding is if you've never done any before, don't worry, we'll teach you from scratch. And if you try and find it really difficult, again, don't worry, persevere, because at some point there will be a sort of a switch that flicks and you will find it a lot more natural. I think a lot of people try it once or twice and see that some people take to it very quickly and get a bit scared by that and think, oh, if I haven't reacted that way, then I'm not going to be any good at it at all. And in my experience, that really isn't true. So don't be scared.
Brilliant. Does anyone else have any questions on the lecture that Dr. Phillips just did, or on any other questions in general, really?
Stunned them all into silence. Oh, no, sorry.
With the coding,
yeah,
you referenced that we would learn Python in first year.
Yeah.
At any point, would we be transferring over to C++, or would we finish using Python as our primary language?
Up to you. So the first and second year modules are in Python. Let me get this right. At the moment, there aren't any taught modules in C++, but certainly most of the particle physics projects are in C++.
Okay.
So if you end up doing a project with particle physicists, you will almost certainly do it in C++. If you do something in condensed matter, then it may actually be Fortran or it may be Python. Different fields use different languages, mainly because that's what the legacy codes are written in. I wouldn't worry too much about the differences, though, because they are different. But once you've learned your first computing language, learning a second is a lot easier. So.
And also, I might just add to that. In second and third year, you can do modules from other schools, and I know that there
that's true too. Yeah.
There are modules certainly with the School of Electronic Engineering and Computer Science. They have C++ modules, so if you really wanted to do that, you could do that.
Yeah. Thank you. Good call. We've had traffic in both directions. Actually, we've had several physics students go there to do C++, and we've had some of their students come here to do Python. So yeah. I've got a question in the chat. No, live lectures are going to be on Blackboard Collaborate. Is there a limit to how much non-symmetry can store information? Good question. Yes, there is, but actually at the moment we're nowhere near that limit. We're limited by technology rather than a sort of fundamental limit. I mean, I drew this pretty picture where I said, hey, the atom here could be up, the atom next door could be down, the atom here could be up. Well, that's great. But unfortunately, there isn't a technology at the moment that can move an individual atom up and the next one down and faithfully store information that way. And even if there were, there isn't a technology that could read it back. So at the moment, we're still, let me get the order of magnitude right. I think we're probably looking at millions of atoms in every bit of information. And of course, in fact, before we get too much smaller, we're going to need to worry about things like quantum fluctuations. There's no good storing information if quantum theory means it's sort of indeterminate how we read it back. So yes, there is a fundamental limit in terms of symmetry, but I think actually both technology and the sort of physical limitations of the quantum world will get in the way first, if that makes any sense. How do you access Blackboard Collaborate on QM+? There is a link from each module's page. So I realize, and I'm sorry about this, I think there were some last minute glitches. Not every module is visible right now. I promise they all will be soon. Or, not that I have anything to do with it. I'm told they all will be soon. But certainly by next week when classes start. But there'll be very, very clear links from the QM+ site. So it's not like you need to go to a separate site. Everything you need for a module should be on its QM+ page.
Okay, I will ask a question, and if you have another question, please go ahead in the chat or whatever. You started your university journey in the University of Sydney, I believe, studying
yes.
studying chemistry. I wanted
That's
to know,
right. Yeah.
what it was that made you decide to choose physics, the better science.
Well, I guess the first thing to say is that the Australian system is a little bit more general than the UK system. So, I mean, yes, I did chemistry in the sense that my I guess the equivalent of my fourth year master's project. It was formerly bachelor's, but it was the equivalent of what you do for masters. So my fourth year project was in a chemistry lab, but I had done, you do more subjects up to third year level in Australia. So I was doing chemistry and physics and pure maths. So it's not like I was not a physicist at all. But I sort of fell sideways really into physics. I mean, I ended up coming to the UK to do, I was looking at PhD positions in both chemistry and physics. And the one that I ended up falling for and deciding to go and do was in physics. And I've been in physics ever since. I think it's, to be honest, there's a very, very sort of porous boundary between the subjects. At solid state chemistry and condensed matter physics are very, very close to one another. And I think there are benefits, whichever side of the line you find yourself on, to knowing a little bit about the other. I mean, you want to know about the fundamental physical laws that govern the way atoms pack together, the way molecules pack together, what physical properties you can expect from materials. And equally speaking, you want to know about how you can actually make those materials in real life, of course. So, I'm very glad to have ended up where I am, but I wouldn't say I turned away from chemistry. I just found a comfortable position to do physics and chemistry at once. I mean, for that matter, and maths. As you will know, it's a very mathematical, it's a very geometric subject as well. So I sort of get to combine all of my intellectual loves in one subject.
Okay.
Thank you very much. I don't think we see any more questions coming through. If there are, please do post any questions that you have in the chat. But if not, there we go. How do you extract information from powder diffraction patterns?
Powder diffraction patterns. Good question. Very briefly, you want to add up around all of those circles, so you get sort of peaks at particular distances, and you can relate that back to the symmetry of the cell, and then eventually to where the atoms are. It's that's kind of a subject in its own right, and in fact, it's part of what I teach in second year condensed matter. But it's what am I going to say? The interesting thing actually is that so much information is lost. So the signal, the diffraction signal, is a wave which is a complex number, but you only detect the amplitude. So you've thrown away the phase. So we've already thrown away lots of information there. And because it's a powder, we've got lots of crystals in every possible orientation at once. We've also lost all the orientational information about which way the crystal is pointing, in a way that we wouldn't if we only had a single crystal. So we have much less information from those patterns than ideally we'd like. And there are lots of really quite clever mathematical tricks we play to try and reconstruct what we've lost. And in fact, I think we're able to do a lot better than you might expect, sort of naively just looking at the problem. We're able to reconstruct really quite precisely what the crystal structures are.
Okay. Right, so I'm going to wrap up, but if anyone adds a question, then we can fit that in. Yes. So otherwise, thank you, Dr. Anthony Phillips.
Thank you all. Have a good welcome, mate.
The boomerang above your head.
That's not deliberate. I should check my background more carefully. Anything else? I don't want students to see behind me.
Yeah, thank you very much for delivering that lecture as well. That was very fascinating. Very grateful for that. And
this should be available, since it's being recorded, this should hopefully be available in future. We hope.
Yes, when we upload it somewhere.
Thank you.
Brilliant. So we're going to restart this. Hello. Again. And now we're going to go into the section of the afternoon. This is the final section. We're not going to go on for much longer. But this is a general Q&A where you can ask us any questions to students about the society, about the university, anything you want. And if there isn't much engagement, we don't have anything else planned for this evening, this afternoon. So
I thought I'd start this off,
Yeah.
just in case this drives up some memories in your head. I would just go through the modules that you'll be taught in first year, and
Yeah.
these guys will fill me in if I forget one.
Yeah.
So in your first semester, you will learn MT1, Mathematical Techniques 1. So that's sort of, you do a bit of matrices, bit of differentiation.
Yeah.
You do a bunch of different
So,
rules, limits.
it's a slight continuation on from it's
got quite a
essentially
lot of
further
A-level
maths.
maths,
Further
isn't it?
maths.
It's
If
further
you-
maths
If
and a
you've
bit
done
more.
further maths, then you will have covered the majority of the content.
Oh, not all of it.
Not all of it. There's also MT0, which is important.
Yeah,
to point out.
MT0, I don't
called
know,
basic
that's
maths,
changed,
isn't
that's
it?
changed
So
from my year two.
MT0 is basic mathematical techniques.
That's literally A level, isn't it?
Yeah, it's not even. It's just to make sure you it's not a proper module. It's not graded as a proper module. It's to make sure you're at the level you need to be at to understand.
You do a test every week.
You do
No,
a test every once a month. It's a once a month test, and it's like it's a pass fail thing. You don't get graded
I
or
think
scored.
if you
on
get
it.
what was it? Well,
You need 30 marks out of 45.
and if you pass that, you don't have to do
And
it
if you
anymore.
pass that, you don't have to turn up to the rest of
If
the
you're really
module.
good at maths,
So
you don't have to.
MT0 is just to make sure that you are at a level where you will understand what's happening. It's not to teach you new stuff necessarily.
And once you
unless there's a
pass the
gap in
test,
your-
I don't think you have to
That's
go
yeah,
anymore.
you don't have to
No,
go
you don't.
anymore. So some people go for the first 4 weeks, take the test, never again.
So there's only gaps in your maths knowledge. and you didn't
Exactly.
get
It's
covered.
to isolate if you haven't covered something specifically or you need more work.
Okay, yeah, so this test is the MT0 basic, is it basic?
Basic
mathematical.
Basic mathematical techniques. You kind of go through some like number theories,
You'll think it's ridiculous.
long division,
You
some
will.
simple algebra.
It starts with like, what does it start with, like percentages?
It starts with like
No,
real
what was it?
numbers.
Yeah, that's
and
it.
then
Integer.
integers.
Yeah.
Definition. You know,
Factorization.
we went into that. Thinking he was just going to be like, "Ha, fooled you," and then lift up the whiteboard and be like, "Here's some differential equations." But it
But no,
really
it's
is
quite
just
simple. Yeah.
just to get
It's
you
to make sure you know the basics essentially, because they have to check.
Yeah. So we've got MT0 and MT1.
Yep, MT1. You've got classical physics, which is
Taught by David Berman.
taught by Professor David Berman. He's a great lecturer.
Yep.
And that is about mechanics, so gravity. You've got like springs,
Planetary.
yeah. So like momentum and angular momentum, velocity and angular velocity.
Yeah.
And then of course there's wave stuff as well.
Yeah.
So
Then is that
Very different.
module was used to be called from Newton to Einstein.
yeah, that
so
was more than
it,
3
it,
years
it
ago.
has been adapted from that, but essentially it's all that physics.
It's like
that's
Before
based.
quantum stuff, isn't it?
It's very easy to wrap your head around because it's still the physics you see in every day.
If you think of Newtonian physics and waves,
Yeah,
that's
essentially
it,
what
yeah.
they have. Have I missed anything in first semester?
And then computing.
There's
Yes, computing. So we've already sort of explained this, but you've got professional skills for scientists, where you will do mostly coding,
Mostly coding and
Python,
a few employability things.
yeah,
as well.
using PyCharm. You'll use PyCharm in that. Where you'll sort of be introduced into Python. It's more than just, they call it introductory. I think there's a little bit more to it.
It is because
Go and do the project,
I think you did A-level computing and you found it quite easy.
Yeah.
I hadn't done computing since GCSE and I found it quite hard. So there's a lot of support there, but depending on how you fall on which side and what
But
You get a lot of time.
All physicists have to learn a certain amount of code, and
Yeah.
this is the certain amount you have to learn in order for your degree to be accredited by the Institute of Physics, and therefore that's why this is a compulsory module.
Then there's a little section.
Like
C.
I know for me
Yes.
at the end of the module, I had to I was given a list of data, and then I had to use it to show weather patterns, and then I wrote a report about climate change or something. It was a while ago for me because I'm beginning third year.
It hasn't changed much.
That was
In ours, we got a large data set and we wrote code to interpret it.
And for you, that will be taught by Dr. Craig Agnor.
Oh, they changed it?
Yeah, Anthony Phillips.
No, Adam, that's good.
He is so good. He taught me year 2 coding. I mean, I can't recommend him enough. I bought him a chocolate orange to say thank you because he's so good.
Wow.
So yeah, I can't recommend him enough.
And that is first semester?
That's first semester of first year.
Yeah.
in your...
Oh, someone's just said, did you say that those maths practice exams
remember,
are
actually.
monthly? So this is MT0.
You only have to pass one.
They're every 4 weeks.
Yeah.
Once you've passed one of those, you don't have to do any more.
And they're not, they're multiple choice. It's a very casual thing. I was only mentioning it just to fill you in on, it's not a joke.
You'll pass.
Yeah. If you don't, then
get a lot of
I'd consider why.
I wouldn't say it. Most people don't pass them the first time,
No.
but after like 2 or 3 times, you'll be fine.
It runs until May, doesn't it? So you've got lots of chances.
It goes on.
Yeah.
So second semester,
Semester.
modern physics
Mark Baxendale.
with Mark Baxendale.
We have interesting opinions.
Mark Baxendale is very quiet. Modern physics is a module about special relativity. So Lorentzian mechanics.
Yes.
So essentially, if I have a rocket ship and I go at light speed somewhere near light speed, somewhere really far away, and then come back, what will happen in terms of time dilation or length contraction?
That module is entirely based around the Lorentz transform. But then it does go into a little bit of the wave.
When it does touch
Heisenberg uncertainty principle. Just a touch.
Just
a little bit. You've also got Our Universe, which is Rich Nelson.
That's really good.
Very good module. If you are the sort of person who does not prefer content and prefers mathematical solutions, you might not enjoy that as much.
There's a lot of proofs in that.
There is some Kepler's laws in that. I find it very interesting, but if you prefer theoretical side, mathematical based sort of stuff,
it's sort of like I don't say prolonged, because that makes it sound bad. It's like a longer, almost like astronomy documentary that covers the big, the small, from the Big Bang to like meteorites and comets. So,
Richard Nelson has actually done making documentaries.
I was watching one of his documentaries the other day. From the BBC Horizon program. Which I'm sure you could find if you looked him up.
Yes, absolutely. What else? That's only 2. You got.
Is the other optional module on this year? I don't know.
So the other optional module was energy physics.
So energy and the environment. None of us did this module. Our universe tends to be more popular. I don't know that you have this module available because of coronavirus, but I'm sure you'll find out. We did. You have 2 options in first.
What's this? These lessons in secondary or college are usually an hour. Did you find it hard to keep focusing in your lectures? No, most of your lectures will be an hour long. There's the occasional 2-hour lecture, but your lecturers will understand. You usually get a 5-minute break. We go across to Sainsbury's across the road, get a snack, something like that.
Yeah, they usually put a 5 to 10 minute break in the middle.
So you won't be.
Yeah, that's not a problem for us. Although you have to remember, we didn't have online lectures. We were
in
person.
You'll be in the comfort of your own home.
True.
So, you can do your lecture from your bed, which that's the dream.
Yes.
Really. Sorry. So there was.
So we were talking about
energy and the environment.
So that's a lot about renewable energy. So the physics behind that, and that module is 100% coursework based. So I think you do a presentation and you write like a long sort of essay kind of thing. I didn't do it, so I can't.
That's optional, that one, isn't it?
Yeah, so you either do that or you do Our Universe. Our Universe is exam based.
Yes.
And energy and environment is
coursework based. Depends how you learn and what your interests are.
Exactly.
Again, we can't confirm because we don't know whether they're running that. They have restricted the modules that they're running due to COVID. But optimistically, most of your optional modules will come in year 2. That's usually just to give you an idea of what your taste might be. If you were on the physics with astrophysics, it is compulsory that you take Our Universe. You don't get a choice in that one.
Another module you do in second semester is Mathematical Techniques 2, MT2, with Professor Marcella Bonner. She's an astro. No, she's not. What am I talking about? She's a particle physicist. At Atlas. That's what I was trying to say.
Which is very interesting because, sometimes, or I don't know how to deal with physical lectures, but occasionally we'd get an email at 1 in the morning from Marcella. I'm not going to be there, guys. Sorry, I'm at CERN. as you do. And it's just like, oh, it's cool, Marcella. Fine, you get back to that important research. We'll learn maths on our own.
But MT2 is heavily you do a lot of integration and differentiation. You do differential equations. You do matrices. I think matrices.
Jacobian matrix.
What else do you do? You two have just done it.
We have just done it. So you do second order differential equations, triple integrals.
Yeah.
You cover matrices.
Do a bit of matrices.
A little bit. That is the main. Complex
numbers.
Yeah,
it's a lot of stuff for those topics.
And that is stuff that you really probably won't have done before. So that is new, and it is mandatory. It is needed. We will. I mean, it's too early for you guys, but we would, say the level of maths required is. Yeah. You need to know that sort of stuff.
If you want some homework, look up de Moivre's theorem, because that's to do with that.
That is.
Do you think signing up as a student ambassador will become an impediment on uni work or revision?
We're both actually student ambassadors.
The answer.
Oh, you are as well.
Okay. Yeah. The answer is no. Unfortunately, from what I have been told,
I received an email from
student ambassadors are not. You're not going to be able to become a student ambassador until semester 2 because of coronavirus, because there's not as much work available.
The problem is there's a spending freeze on, so that the student union is not allowing the departments to spend any more money than they already are. So we've been told that they won't be hiring new ambassadors. There's going to be less work available, so they want to give, rather than give everyone one project from now to Christmas, there's going to be a few more, but they are intending on having a hiring session.
But it didn't get in the way. That's all that it is.
Physics ambassador is you choose your hours.
Yes.
Same as student.
A lot of the hours are on weekends.
Yeah.
None of them. I mean, some of them are during lecture time, but you don't choose it.
You don't choose it. You choose what you have in the gaps in your timetable.
Exactly.
It is, and there's other student work on. We should mention there's other student work available to you through the careers department. So they are located in the Octagon. I'm not sure what the situation will be with that for first semester.
Yeah.
But if
check out the website.
If you if you're struggling financially, if you just want to get a job, part-time thing, they'll help you out with that. They'll make sure.
Will PASS be? Yes, PASS is now fully online via Blackboard Collaborate every Wednesday from 1 until 2 o'clock, and you can access that via the PASS page on QM+, which you can access in modules. Maybe you want to pin it. You can pin modules so that they come up on your home screen. You might want to do that. Okay, yeah, we're good. So yeah, that's still available.
Yeah, that's all good.
How does the workload outside
lectures compare? So homework is that. So
there's less homework.
There's less
homework, but
in
you will.
Yeah.
So foreshadowing.
There's only 3, wasn't there, per module for us, for most of them.
That's right, in year 1.
Not too bad.
In year 1, per module, you only have 3 homework. So I reckon that works out. You'll have 1 piece of homework roughly per week.
They're only about 6 questions as well. Not
however,
there isn't a lot, but it is.
They can be quite hard.
It does count towards your first year grade.
And
so
grade.
Usually it's not much. Usually over the
20%
semester, all the homeworks add up to be 20%.
Yeah.
So each one isn't worth a lot, but it is the only reason they do that is so that you actually do the homework, because a lot of universities don't have their first year as a graded year. Or it doesn't count towards your final grade, and the homeworks don't matter, and then students just don't do it. So the way that QM did it was count it for a tiny amount, and then that's just so that you care a little bit.
Yeah, and then anything else is up to you, isn't it, really?
Yeah.
How much work you want to put in.
Also, even if you're somehow don't feel like doing the homework for some reason, you really should, because homework questions are the most likely questions to be in your actual exam.
That's right.
So even when you're revising for your exam, doing your homework again.
Yes, in fact, sometimes the homework questions do turn up in the exam,
Yeah,
with a number change or something like that. So it
it's worth it.
It does.
You might have mentioned this earlier, but I just wanted some confirmation. If COVID wasn't happening, when would the physics annual report have occurred? In reading week of second semester, which is very late February
very start
and
March.
very start of March.
Yeah.
I think it was the
usually.
March 2nd, was it?
So
this year?
ours was
Something like that.
March this.
Yeah,
I think ours was March the 3rd until 7th or
something like that. Yeah, it was-
Yeah,
I
something like
can't
that.
remember now. But yeah,
Yeah.
we went abroad for 5 days. The trips are usually 5 days, so that when you come back, you have some time to do homework. or
Yeah,
whatever.
absolutely right.
But enough time to have fun.
Yeah.
On our trips abroad, we don't hold your hand. You are free to. Other than
The way
main,
that the Ukraine trip worked was the only event that was actually planned by PsiStar was the trip to Chernobyl.
Yeah, that was one
So
day.
we were there for 5 days. The Thursday or the Wednesday was Chernobyl day, and everyone, that was the whole day.
Yep.
But other than that, we went around the city. We went to go and
Yeah,
see the
we
sites.
split
We
off
went
into
going
different
out,
groups
and
and
we could go
things,
to the
yeah.
bars and drinks and in
We-
the evenings and stuff like that.
we treat you like adults because you're not at school anymore. And much like with I was told this in my first week at university, and I think it was the best advice I was given. I was given it by a lecturer, I can't remember. At university, it's up to you. No one cares if you don't work hard. The only person, it's up to you. If you want to get first, work hard. If you don't mind so much and you just want to go for the uni experience, that's up to you. You are now an adult and you decide what you want to do.
And the fact is, your lecturers aren't going to, your teachers probably said this, they're not going to chase you.
They won't
If
chase
you, if you don't put your homework in, they don't care, but they're not going to give you, they're just going to respond exactly how you expect.
So this is your opportunity to do what you want with your 3 or 4 years at university.
Absolutely.
It's your money at the end of the day.
Make the most of whatever you want to get out of it.
Should we email Psi using our personal or uni emails? Depends, because we will send out, if you only want to be added to the WhatsApp group, then whatever, but whichever email you want us to email you back on. So if you're okay with us being in your personal email, do that.
Yeah.
If you'd rather that your uni web status, all uni stuff, use your uni email. I'm not sure if yours will all have been generated yet. They should have been, but I know that mine wasn't generated. Mine wasn't generated until like a week into term.
If you want, you could join with both. We don't mind.
Yep.
We'll email both
Yeah.
of you if you want.
Yeah. Again, that email is QM
PsiStar, so that's PSISTAR at ampersand QMUL dot not at gmail.com.
Yeah.
Wait, what?
It's at gmail.com.
But you told everyone else it was at QML.
I gave you the wrong email earlier. Okay, it's at Gmail.
Look, follow us on Facebook or buy our membership. Please buy our membership, and you'll get links to everything. It's all. We do try and keep links to everything else on there.
Yeah, cool. I'll put it
Can
in
I put it in
chat.
the chat or something? Yes. He will. Please do keep any questions coming in. I think we covered all the first year modules,
that's definitely right.
didn't we? We didn't leave any out.
Yeah, no. So unless you want to hear about second year,
labs,
or
but I don't know if
whatever.
they're
Oh yeah,
labs. Good point. I'm not sure how those
I
will
don't
run
know if
for
they're
you.
normal this year.
It's semester B, so possibly.
Oh, is it?
But
us it is.
labs for so the lab is a coursework based module. You do several projects and they all count for a fairly big amount.
Yeah.
So most you might do 6 projects and they'll all be roughly 15-20% of your final grade. They're all fairly basic sort of stuff. It's unfortunate, but second year labs is where it gets more interesting. First year labs is in general sort of just the basics of electronics and mechanics. It's stuff that you've covered already, isn't it? So.
First year labs are. I'll answer your question soon. First year labs, well, all labs actually. It's not how you do the experiment. It's how you record your results.
Yes.
You'll be given a book, like a writing pad book, and you have to keep it up to date. It's to do with how well you show yourself, how good of a scientist you are. Do you make diagrams of your equipment?
Yeah.
Do you make nice tables? Do you put the date? 'Cause the date. If you don't put the date down in real life and then someone else invents it, you could lose the
They've
copyright.
got there's a story that they'll tell you about that.
That's
where
it.
there was.
It sounds scary, but it's actually not too bad.
Where somebody lost
Tons of money.
They missed out on £1 million invention because they didn't have their lab book properly done.
Yeah.
But yeah, that's the labs module. It's,
And then and second year labs is better. Like in second year labs, you'll get the opportunity to do Anthony Phillips, what he was talking about, neutron diffraction. You'll get to do that. You get to play. No, X-ray
X-ray
diffraction.
diffraction, isn't
You
it?
get to mess around with an X-ray diffractometer, and that's
Like,
good
you get to
fun.
build a helium neon laser,
you do.
stuff like that.
Sounds
You
good.
see, this is the stuff you hear
You
about.
build
And
the
this is
laser.
why. This is why we do it.
I mean, there's just loads
There's
of
loads of stuff. You can check. You can actually read up on the. You should be able to read up on the module on QM Plus. Just have a little look around on there, and you might be able to find it. Someone said, "What's the latest time you can change course if you find physics isn't for you?" Well, I can't figure out why physics wouldn't be for you, but if it's not, you have to consider how much content can you catch up on. So, if you can move laterally to some extent. Speak to the uni, get in touch. I definitely wouldn't recommend doing it from after more than a month. Otherwise, you're going to have way too much to catch up on. So if you decide in the first 2 weeks and you're like, no, this is just simply not for me. No, I made a mistake. Then yes, email. I'd say Harvey, possibly, or possibly just SPA.
Well, I mean, there's two questions that you've kind of asked. One, if you wanted to move between courses within the School of Physics and Astronomy, i.e. you were like, I want to do astrophysics, that you literally can do that essentially up and, well, even past then. You can do it as long as you've met all of the prerequisite modules for that degree. i.e. if you didn't do our universe, you then wouldn't be able to switch to astrophysics. But like for theoretical physics, all you need to do is MT3, and you can and physical dynamics, and then you can even change in year 3, say. So all you have to do is you have to sign a form.
If it's a different course within the School of Physics and Astronomy, that's really email. That's just an email, and they can put them wheels in motion. But if it is to a different science or
if it's
an
outside
engineering
of the school,
or something like that.
If it's outside the school, I don't know, because I'm not actually aware of anyone ever having done that in my time.
I think a few people did it on our course. A few people switched to an engineering degree or something like that.
It's harder.
It's harder, but the option's there for you. Just the sooner you figure that out, it will be better, because even now there'll be content which will be going out. There'll be emails, welcome emails, stuff like that. So don't leave it too long. Otherwise, you'd run the risk of having to do the whole of the first year and then rejoining whatever course you want to then.
What is the usual cost of the annual trips? About £330. We missed it.
It varies. It does vary.
It's usually not too much. I think last year was about £350.
I think it was
$350. It's been more and less in the past, probably.
Yeah, it depends what we do, really.
Depends where we go.
What? Thank you.
Depends where we go. Kiev was quite cheap, wasn't it?
Kiev.
That was a 5-day holiday. Remember?
I think
that was,
including like the trip to Kiev.
The hotel, the flights,
to Chernobyl, the hotel, the flights, the taxis.
It really does depend on what we do.
And when we were actually in Kiev, everything was insanely cheap.
Yeah, it was.
It's one of those countries. When you go to Iceland, their economy means that everything is expensive. Like your food would cost the equivalent of £10-15. Your drinks, anything, fuel, everything is expensive there. Whereas in Kiev, it's the opposite. You go there and a drink is £1, and food is nothing. And
I think a pint was 50p at one of the pubs.
I mean, we were having like 3-course meals for £3.
So
it was great.
It really did.
I think didn't their metro system there was 50p to ride?
30p, wasn't it?
30p to ride, that was it,
30p.
The tricky thing is, it's close to Easter when our reading week is, and obviously reading week is when we go abroad because we don't want you missing your studies. So there's not a lot we can do about timing. So that puts the price up a little bit, but I defy you to find many places where you can stay for 5 days. I mean, like, think about it. Even if it didn't include flights and all that, that would be like, just say £60 a night, and that's like a hotel cost, say. So
it really does depend. But we're aware that there's a snow sports society that also runs a ski trip, and that is so a ski trip naturally costs sometimes upwards of £1,000. It's an expensive thing. We're aware that you as students don't have that sort of money.
Yeah.
We usually want to
that.
get about 30 people on the trip to run it, and
Yeah.
so we try and keep it as cost effective as possible, but we'd make you aware of how much it roughly was going to be before we announced it. Is there any more questions before we wrap this up? Because I think we're going into, we can't actually use this room past 4 o'clock, but
The battery's getting low.
my computer is running out. So yeah, if this ends abruptly.
Anything else?
If not, I think we're going If not,
Check out our Instagram.
oh yes, the Instagram. Please do.
Our
I'll
oh
answer
no, what have I done?
that. You've only
Okay,
clicked
cool.
off the main thing.
Um,
Is the annual ball for all physics students?
It's
No,
not-
it
it's
is
for
a.
anyone.
It is a PsiStar thing, so it is our
It is-
society ball. But obviously, if you anyone would be welcome if you want to bring a guest, if you had friends. It's just the sort of thing like that's why we encourage people to buy the membership. It's just so you can. Yeah.
That's the Instagram handle.
That's the
It
Instagram.
won't let me put an at. There you go.
So usually, especially with our lectures and stuff like
Are we
that.
off the meeting?
No, we're still there.
No, we're still there. Look.
Good. Can you hear us?
You can hear us all, can't you? Yeah.
I hope so.
All right, good.
Yeah.
Sorry,
fine.
it looked like it kicked us. That was all.
Yeah. So no, with the lectures, we don't want it to be like we're checking on the door sort of thing.
That's right. Yeah.
Yeah,
James
James
is
got
correct.
it.
Yeah.
Yeah.
Yeah. We purposefully do that to encourage people
James.
to join.
Yeah.
Essentially.
Please buy. Like I said, the membership is
It's
only
so much.
£5.
It is really good.
It
fun.
is such good value, and it really helps us. Please buy that.
Oh, I think
Yeah. There is no IG name for the society.
there is. James.
Hey, thank you.
Hey, James. That's the Instagram. Perfect. Anything else? We hope you've enjoyed the event today as well. This was, this was a pain to organise because we did really want to run this event as a physical thing.
Yeah, we were
And
going
then
to.
things
but,
changed. How important is having a Facebook to uni in general, or to the society, or your social life?
I would say this: it's not that important. I mean, because obviously you can
No,
follow.
we
You
get
can. You can.
Oh, to uni? No, it's a lot of your societies have one.
The only thing I would say is I have found that a lot of people from outside of London only use Facebook Messenger, whereas a lot of people from London use WhatsApp.
That's true.
So you may find a lot of your friends only use Facebook Messenger. That really annoyed me, being a Londoner. I was like, what do you mean? No one uses Facebook Messenger? But apparently,
Yeah.
people
It'd be
outside
helpful.
London-
It's not like you're going to not be able to cope without Facebook.
No.
By any means.
The mailing list is fine, isn't it?
Yeah, absolutely. So
So email us instead.
yes, email us at qmslistar.at
Someone already has
At-
it.
gmail.
Good.
There we go. Got it.
Nice.
Yeah. If you do have any more questions, email us.
Yeah,
All
feel
our
free to
emails are on the website, or email QM or send us a message on Facebook. You can get in touch with us.
Cool.
Yes.
Right, let's wrap up.
Let's wrap it
Right.
up.
So unless anyone bangs a question in quickly.
Yeah.
It was
Thank
Thank
you.
you. You're
Right,
welcome.
you're very welcome.
Yes, we do hope to see you at events. And look out for David Berman
David Berman.
interviewing
Malcolm Perry.
Malcolm Perry. Yeah. Thank you very much for coming today.
yeah. Thanks for attending.
And goodbye.
Bye bye.
Bye-bye.
See you at our events.
Yeah, see you later.
Buy our membership.